Check one. Okay, I have more up here too. They have an assortment. Good morning, everybody. Welcome to day 2 of CABW. Today's a slightly shorter day, and reminder, we're ending at 12 for lunch. One of the talks in the afternoon, I keep saying afternoon, second session of the morning is not happening. So we're gonna end 20 minutes earlier. And then there's the workshop with Ryan Peak at Fish and Wildlife, the R workshop. So I think that's full at this point. No more last minute attendees. So anyway, and that'll be in the Klamath room. So there's lots of signage and it's that way. Okay, so we're gonna kick things off our first session. Let me grab my agenda so I have all the speaker notes. And Laura, you are up first. So Laura is gonna be talking about developing flow ecology curves to assess ecological risk to flow alterations in the North Coast. I'll give you your quick little intro and you could come on. And like I said, you can choose your mic option. Here it is. Okay, so Laura is a freshwater ecologist with expertise at the community level. Her research centers on the drivers and dynamics of bioindicator communities such as algae and invertebrates in the context of specific management scenarios such as flow. There's more here, but I'm going to do the truncated version. And here's this, if you'd like. Your necklace, and then just push to start. Okay. Cool. All right. Well, let's get this show on the road. I always like to start the morning off talking to a bunch of people. It's usually just my dog, but here we are. So yeah, thanks for the introduction. And I'm going to be talking today about some work that I've just gotten started on. I started here at Scorp just about 6 months ago. We've been looking at developing these flow ecology curves to address ecological risks in terms of flow alterations in the northern coast. And it's really kind of exciting to be a part of a project that gets to touch back to the North Coast because I did my master's in Humboldt and got to work on the Eel River. And I got very intimately familiar with how flow shaped some of our very special communities, including our algal communities. I took this picture here on the Middle Fork Eel River many years ago. And wow, we're going to know which direction's which. The impetus for this project is really getting at how can we better assess ecological risk to flow alterations. Stream flow alterations have, of course, been posing a risk to many of our salmonids and other sensitive species for many years. And of course, there's continuing to be different alterations taking place both now and in the future. And traditionally, environmental flow methods are generally really restricted to the site they're developed on, which really prevents them being implemented at a larger scale, such as within a region. They also require a vast amount of data and are often only addressing one species of interest, which kind of really limits their implementation. And this has really driven the need for an approach that's much more scalable, that's considering multiple species, such as our bioindicators like our macroinvertebrates and our algal communities, to really evaluate the full risk of stream flow alteration and allowing it to be applied at even unmonitored reaches. So there has been kind of this drive to take a more integrative approach to assessing ecological risk. And this framework kind of utilizes 3 forms of evidence to get at this. The first being functional flow metrics, which I'm going to touch a little bit on here today, and kind of drives the other 2. These are kind of way to get at how the hydrograph should be considered in terms of its importance in shaping the ecosystems, both in geomorphic ways and ecological ways. And then through those functional flow metrics, we can examine how our invertebrates and algae might be shaped by changes in these key aspects of the flow regime, as well as our species of concern, such as our salmonids, or in this case, the yellow-legged foothill frog. And today I'm going to be focused just on number 2, but if you have questions about the others, I can definitely put you in touch with those folks, and happy to chat about it. And we're utilizing the North Coast as our test case because this is an area that is definitely likely to be further impacted by future flow alterations. And it is, of course, a stronghold for many of our salmonids. And so it serves as a natural starting point in many ways. But of course, we'd like to explore testing these approach out in other regions of the state. And I don't feel like I have to really say this slide, but it is an important starting point, is the flow, of course, defines the salmon habitat in many different ways, be it those peak flood events that are really going to help the salmon key into when they should be migrating and spawning, and also those spring periods when the flows are starting to decline is a key period for when the floodplain is available for rearing habitat. And this has obviously been a way that they've developed those functional flow metrics to consider these different parts of the flow regime. But it's important to therefore think about, okay, we know that the flows are important for our salmon, but of course, they're also important for our indicator species, such as our algae and macroinvertebrates. This has actually been something that was well studied in the North Coast. A lot of folks from Mary Power's lab that I had the pleasure of working with taught me a lot about this. And there's, of course, those peak flood events that can be very critical for the algal community and the macroinvertebrates because they can flush out those fine sediments, but also flushing out large resistant predators. And I mean resistant to like predation, such as our large case limnophilids. And then in that spring period is a critical time when the algal community really starts to develop and take off. And then slightly after is the invertebrate grazing community. And then, of course, that dry period is really going to be when you see a shift towards potential algal senescence, which has implications for cyanohab risk. So with all of that in mind, it's important to therefore explore the functional flows a bit better because there are so many pieces of the flow regime that these communities are influenced by. So just to give you a bit more background on these functional flows, there is these 5 components that we're considering, the first being the fall pulse, then those wet season peak floods, the wet season base flow, that spring recession limb, and then finally those dry season base flows. We further refine those down into key metrics of interest, being often magnitude, timing, and duration within each of those components. There are additional metrics to consider, but those are the primary ones. And this has been a well-studied approach. It's been repeatedly shown to be important for both geomorphic influences as well as ecological ones. And it's already been examined in the context of our bioindicator communities, at least at gauge sites. So they found that both of our algal and invertebrates were responding well to changes at gauge sites across the state by combining bioassessment data with long-term flow data. But if we wanted to zoom into a region, we can see from this map that there's just not enough gauge data to actually look at this. So we kind of need to take a slightly different approach. So just to give you a broad overview of the approach, this is kind of leveraging the bioassessment program, utilizing the ASCII and CSCI, and then utilizing flow models to generate functional flow metrics. And then to reduce the number of functional flow metrics to concern, we're utilizing a 2-fold approach. First, utilizing boosted regression trees to look at which ones are most important to those metrics or those indices. Then utilizing generalized linear models to actually develop the curves and also further refine which functional flow metrics actually have a good fit with those indices. And that gives us kind of a reduction in the number of functional flow metrics to be considering. So let's get into some results in brief. So what we note from the boosted regression tree is that the top indicators, functional flow metrics to consider for our algal communities is definitely that 10-year flood magnitude being a very important predictor, followed by 7-day minimum timing and dry season high base flow. Wet season duration is grayed out because the generalized linear model did not have good model fit. So it suggests that those high flood events, dry seasons, are really critical. For the invertebrates, it's a slightly similar story, with again a 10-year flood duration being very important, 7-day minimum timing again, and then full pulse timing. So this suggests that potentially the invertebrates might be responding more so to timing and duration, while the algae is more responding to changes in the magnitudes. The scouring floods definitely seem to have an influence on that probability of achieving good ASCII. And then as a reminder, good ASCII is that threshold of 0.86 or higher. And it seems like the curve really shows this. And I want to be clear about that y-axis because it's a little confusing. It's a relative change from unimpaired conditions. And so you're starting from negative 0.5, which is a 50% reduction in the 10-year flood event. And you can see that the chance of achieving good ASCII really increases as you get closer to 0. So if we have those reductions in flood events, this can be pretty detrimental potentially. And then in terms of our earlier timing, or timing of your lowest flows in the dry season, does seem to be very critical for both our algal communities and our invertebrates. The x-axes here are slightly different, and I want to emphasize that basically as you move into the negative direction, that means this is an earlier low flow period versus in the positive, it's later. And so again, you can see that if we have these earlier low flows, the chances of achieving a good score for both algal and invertebrates really potentially declines. And so this rather confirms what we were expecting, that those periods of strong flood events are very important, as well as that dry season period, as that has been found in the literature previously. And so just some final takeaways. The algal community seems to be generally responding more so to changes in the flood magnitudes, while the invertebrates are more so responding to changes in timing and duration. Dry season base flows and the timing of those lowest flows are likely to be the ones most altered by diversions, and also the ones that management can most likely help contribute to regulating. So it's good to key in more so on how these indices are responding to those. And it does seem both of the communities are rather sensitive indicators of these dry season alterations. But I do want to emphasize again that what I presented today is just one part of a larger framework. These curves will ultimately be used alongside habitat suitability analyses for our sensitive species to really assess fully the ecological risk of flow alteration, generating maps such as the one I'm showing you here to really get at how much flow can we actually take out to keep our good conditions. And this approach ultimately is relatively flexible in nature. It can be readily applied to other regions as long as there's sufficient data and other potential flow alterations. Of course, in the North Coast, we're talking about primarily distributed diversions throughout the watershed due to cannabis cultivation, but there's other aspects such as flow regulation due to dams. And we could examine not only the current risk, but also future risks due to changes in different flow alterations. With that, I'd love to thank my larger project team. It's been a really great learning opportunity to learn from so many experts in this field. And with that, I'd like to end on another picture that I always love to think about fondly of. So with that, I hope I can take some questions. Thank you.
Great, thanks, Laura. We do have time for questions. So questions from in the room. Anyone? Question in the way back.
In this study, have you or do you have you considered modifying or combining these curves with seasonal temperature data?
Yeah, that's a great question. So you're saying like combining the influence of temperature on these indices as well as flow?
Yeah, I'm curious how that influences the benthic macroinvertebrates and also the algae.
Yeah, it's a great question. It's sort of outside of the scope of this project, but I'm actually working on another project where we're actually looking at the effect of flow and temperature together on biota. And it's actually also one of our case studies is in the South Fork eel. So stay tuned. I have more to share on that. So yeah.
Thank you.
Hi, thanks. Great talk. This is kind of more open-ended, but at the very end, you said, this is reproducible in areas where you have enough data. Do you have an idea of like how much data you need in a region to create these kind of curves or to do similar analyses?
Good question. Yeah, so you definitely need, obviously, a sufficient amount of like flow gauges to be validating a flow model on with obviously I think it's generally like several years worth of flow data. Like what I noticed was some of the reasons we didn't have all the functional flow metrics was there just wasn't sufficient data to capture those. So you do need a sufficient amount of gauges to validate that flow model on. And then in terms of the bioassessment data, I think we were kind of coming up to the bare minimum in some cases with some of the sites. So I think you definitely need at least about 50 sites or more with bioassessment data, because once you're going down, it's just like the amount of uncertainty in those curves really starts to increase. So yeah, that's where I would imagine the bare minimum would be.
Any other questions for Laura? Anything online? Ooh. You can turn the mic on too, or yeah, use the orange.
Okay, so the question is, how is good condition defined?
Great. Yeah, I may have not said that most clearly. So good condition is based on the thresholds defined for achieving like the reference of both the CSCI and the ASCII. So an ASCII score of 0.86 or higher, or a CSCI of 0.79 or higher. So meaning that that site is likely, based on those indices, intact. That was defined previously by others. So I recognize that I'm kind of leveraging y'all from yesterday's. So I could have explained that more clearly.
And we have one more. You mentioned unimpaired flows. Does this relation and models only work for unimpaired flows? And how do you know if a flow is unimpaired?
Great question. So this is actually I should be clear that it is based on both unimpaired and actual, and what we're looking at is the delta in the change of each of the functional flow metrics between unimpaired and actual. And unimpaired meaning based on like reference gauges, so sites where we know they are in reference condition. So that's where like the unimpaired part comes from, and it is based on this flow model that was generated by the Nature Conservancy and Upstream Tech. So I would definitely defer to them for further details on that. I'm not a hydrologist, but that is my general understanding.
Awesome. Well, thank you, Laura. Goodie bag. All right, so now we're going to kind of shift gears into estuaries. Woohoo! And first up, we have Kevin O'Connor, who's going to give kind of the part one of the estuary talks and provide an overview of California's statewide estuary monitoring program and linking that to the bioassessment community. And then you know how to run all the things. Let me give you your formal intro. Kevin O'Connor is an environmental program coordinator and coastal ecologist specializing in wetland restoration, monitoring, and assessment. Woo woo!
Okay, we're there.
And serves as the program director for the Central Coast Wetlands Group at Moss Landing. All right, all yours.
Thanks, Allie. Thanks. Whoa. I won't speak too loud. Okay. Okay. Is that better? A little better? Okay. Thanks for the intro, Allie. And thanks everybody for coming for day 2. A few more thank yous. First, I want to thank CABW for having this three-part estuary series. I know we usually are talking about watersheds and bugs up in watersheds, but we're moving down to the bottom of the watershed where it all comes together in the estuary. So as she said, this is a three-part series. I'm going to do an overview of the EMPA monitoring framework. Eric's going to dive into some efforts on the South Coast for a Sentinel network monitoring program, and then Jill's going to dive into eelgrass monitoring. So we're going from big and focusing down to the smaller. Also want to thank the overall team. This has been a collaborative effort over the past 5 years amongst multiple institutions on the South Coast. We've got SCWRP, CSU Long Beach, UCLA. On the Central Coast, we've got CCWG at Moss Lane Marine Labs. And then on the North Coast, we've got Sonoma State as well as Bodega Marine Lab, all working together. Oh, along with the SFA Water Board, developing this monitoring framework. We put a lot of work into it and just really proud of the work we've done and excited to show it to all of you. Estuaries, aren't they beautiful? So California, as you know, we have a large latitudinal gradient from way in the north all the way to the south. Along that latitudinal gradient, we've got tremendous diversity in hydrology, morphology, and ecology of estuaries in California. And that results in a variety of estuary types. So you can see on the left, we've got coastal lakes and lagoons. Up on the north coast, these are mostly freshwater systems divided from the ocean with a beach berm with a small watershed. We've got our large embayments and bays like Tamales Bay or Drake's Estero. These are perennial systems, always open to tidal action. We've got our larger river mouths that seasonally close up to ocean action with the formation of a beach berm. So some of the year they're tidal, some of the year they're not, turn into freshwater systems. And of course, we've got our small stream mouth and coastal estuaries. Altogether, there are over 500 coastal confluences in California, excluding the SF Bay, which has, of course, a whole bunch more. But we're really focusing on the outer bay, not on the SF Bay. Outer coast, not the SF Bay. So there are many decisions that affect what happens in estuaries, ranging from flow management upstream, mitigation within and around the estuary, nature-based solutions to address development within and around estuaries for sea level rise, climate change, restoration actions in degraded estuaries, and potential contaminant discharge. And all of these decisions for effective management of these estuaries requires consistent monitoring and assessment, which is something that hasn't really been available to estuaries in California up until now. But why are we here? Why are we presenting on estuaries here? Well, the statewide 305B and 303D integrated report largely neglects estuaries. This has been due to a lack of consistent assessment framework and protocols and data tools for estuaries. But the statewide EMPA monitoring program hopefully provides the necessary elements to include estuaries into the statewide bioassessment program in the future and into this the integrated reporting. But we all are going to have to figure out how to do it together, how to make this happen. So taking a step back, there are obviously challenges to large-scale monitoring in any type of system, but especially estuaries. As I said before, these are highly variable systems going from north to south, depending on size of watershed, stressors going in. So comparison of data across these heterogeneous environments is quite difficult. So coming up with a framework that allows for that has been an issue, but we think we've found a path. There's obviously different management needs for different estuaries along the coast. You've got different owners, you've got different managers, you've got different stressors, all that comes together with different management needs. There's a variety of existing monitoring programs in California focused on estuaries. So for example, in the South Coast, we've got the San Onofre Nuclear Generation Station Mitigation Monitoring Program, SONGS. We've also got our NERS and our NEPs. We've also got strong, large efforts going on in the SF Bay. But these various programs don't necessarily speak the same language, don't necessarily talk to each other, use the same online data systems. So that's kind of haphazard and not really altogether synchronized. And of course, there is the ongoing question of data storage and sharing. Where's all the data going to go for a statewide monitoring program? How will it be uploaded? What's the QA checks? How will it be downloaded? So we've been working to address all of these various issues through the development of this program. In 2022, the Decadal Management Review completed the first comprehensive evaluation of the entire statewide MPA network, and the state was unable to include estuaries in the review because there was no consistent assessment method of the condition of ineffectiveness of estuarine MPA designation in California. In 2020, OPC funded this collaborative group to create the California Estuary MPA Monitoring Framework and Program. And we've been working ever since to really build out that program. And just as a heads up, of the 124 MPAs in California, 23 of them are actually estuarine MPAs. And here you can see a map of those estuarine MPAs from the north coast all the way down to Formosa Slough in the south. So the impetus behind the development of this program was MPA designation, but since then we've really spread it to just an overall statewide estuary monitoring program. So the goals are to monitor California estuaries with a standard, comprehensive, function-based assessment framework to determine the health of California's estuaries and the efficacy of MPA designation. And monitoring has been occurring consistently since 2021. And beyond that MPA designation, there's a suite of other questions you can address, such as how healthy are California's estuaries, and is the health improving over time? What are the key stressors impacting our estuaries, and how resilient are the estuaries to those stressors? And then how effective are our management measures, including restoration, mitigation, and regulatory protection? So here's a map of the sites that have been assessed so far using the EMPA monitoring framework. And this is across multiple programs. So consistent monitoring of 15 to 33 sites. So we started off with 15 core sites, and we've added to it over the years. Since 2021 in the north, the furthest north we have right now is 10 Mile River. Furthest south is down in Baja, actually. So this is representing the EMPA monitoring program, the Southern California Bite 2023 regional assessment, and then efforts down in Baja. And you can see the estuaries represent both protected and non-protected sites and a variety of estuarine types. So we've got perennial open estuaries and temporary closed estuaries. And the different colors represent those. On the north coast, you can see there's a big hole up there with nothing. And we've been working on that. We've been doing outreach to folks at Cal Poly Humboldt to hopefully pull in some estuary monitoring up there, some tribal engagement, and then there's a restoration project going on at Redwood Creek with multiple agencies actually, and we're hoping to get the framework adopted at that estuary. So we're kind of dipping our toes into North Coast. This estuary monitoring program consists of several elements that together can address key management issues and these things we've developed over the years. So we have a key assessment framework, that is the function-based assessment framework, a suite of standard operating procedures. We didn't develop new SOPs, we really adopted SOPs and pulled them into the framework. So we have consistent data collection at all the sites, a data management system, so all the data is going into one location, it's got QA checks, it can be pulled back out. A standardized sampling design, so when you get to the estuary, you know where to do the sampling, how to do the sampling, how often to do the sampling, so it's easily repeatable. And then an implementation strategy. We've got all these tools developed. How are we going to roll it out across the state? There were also 4 key factors that we kept in mind as we were developing this framework that we set out from the beginning. That being that the framework should be flexible and module and function-based approach. So due to the variety of estuary types in California, it has to be able to be applied to all the different estuary types and the different management needs. We have to have that, ensure that the data are comparable and can be synthesized across this large geographic area. The data are interpretable, so we have comprehensive and consistent sampling through designated SOPs, and that the sampling framework is practical. We don't want the sampling to be overly onerous so that smaller groups or various agencies can't go out and do the sample collections. So we've set a 3-day sampling time frame. We do it in the spring and in the fall. You go out to an estuary, you're there for 2 to 3 days, you complete all the SOPs. And with this, you can utilize the information for, oh my gosh, baseline, I gotta go a little faster. So getting into the function-based assessment. So the underlying principle behind it is that all estuaries provide a variety of ecological functions at some ideal rate in the absence of anthropogenic disturbance and alteration. So we're not looking at specific habitats or species, we're looking over overall estuarine functions. And the project team selected 9 individual functions, as you can see here, to start off the development of the framework. Those are ranging from primary and secondary production to various habitat provisions, shellfish support, and larger things we're looking at overall marsh plain vascular plant support and sea level rise amelioration. And we ensured that the frame was adaptable to a variety of system types and management needs. So again, modular, so that program agencies can prioritize functions for inclusion based on program needs and estuary type. You don't have to assess all the functions, you can just assess the functions of interest. Flexible in that multiple indicators can be used to assess the given ecological function. You're not set to a single indicator. and it's adaptable, and that functions can be added or removed over time. The formatting got weird on this, sorry about that, but this is the big matrix that brings it all together. We've got our 9 estuarine functions on the left and the suite of indicators across the right, across the top. And for each of the green boxes, that's the linkage between the individual indicator and the function of choice. And for each of those indicators, we develop condition statements that when addressed and analyzed and summed together, you have a score for each of the functions. Just for example, you have support of vascular plants. We've got 5 different indicators that roll up into that individual function. I want to show a slide that shows the indicators a bit better. So they're grouped into abiotic functions or indicators looking at water quality, sediment, and topography. We've got biotic indicators looking at the benthic infauna, fish, and invertebrate community, as well as algae surveys and SAV, and the vegetation community. And then finally, general community composition. We've got eDNA and general habitat condition. And when we're going out and doing this, we're running all these at the same time, but that's not necessarily needed based on the functions of interest. We developed an integrated data management system, empa.scorp.org. At this location, you can download all of our reports. Data can be uploaded and QA checked. Data can be downloaded. We've got links to all the various programs that are utilizing EMPA, as well as all of the SOPs, field data sheets, and data templates, all available at one location. All right, getting to why we're all actually here. So bioassessment. So there have been previous efforts to develop bioassessment tools for brackish water habitats through the kind of adoption of marine-based bioassessment into these kind of estuarine habitats. One example is in the SF Bay, the development of the MAMBI. However, these previous efforts have really focused on subtidal habitats, whereas we're looking at more intertidal and hopefully marsh plain habitats for the development of bioassessment tools. Now, as I've said, we've got a whole suite of different SOPs we're collecting data on, and a future bioassessment tool could be based on a suite of different indicators. So we've got plants, SAV, benthic infauna, algae, fish, or it could be some kind of multi-metric index yet to be determined. But of course, to start off, you need to have consistent monitoring, and we're really hoping that the EMPA and the statewide estuary monitoring program can serve as that baseline data. Currently, it's being used for condition assessment and, of course, MPA designation. But going forward, after multiple years of data collection, we'll have kind of a large enough data set that we can start building these bioassessment tools in hopes of collaborating with folks in this room. And I just want to say we've started dipping our toes into it a little bit. So there's a Nepton habitat utilization scoring tool that folks are working on down at SCORP. And you can see there's individual metrics along the bottom, DO events below 3 milligrams per liter, percent of temp above 25 degrees C, different metrics that we can score for each of these estuaries that can then be rolled up into an index. And if you have more questions about that, you can ask these two people, Eric and Jill, because they know more about it than I do. But you say, Kevin, how is this all going to work? How are we going to implement this large-scale program? Well, we've been working on that on multiple fronts through various different projects. One, or incorporating assessment protocols into state, regional, and local programs. So we've got the EMPA monitoring program as the core, but then in Southern California, working on a regional monitoring program that's utilizing the framework. Monterey Bay, we have the Climate Resilient Monterey Bay Regional Monitoring Program. We're adopting the framework as well. So we're trying to get this framework adopted into these various regional and local monitoring programs. Use of the indicators and protocols and permit monitoring requirements. So we've been working with the Coastal Commission, the Coastal Conservancy to get these protocols adopted into permit compliance, and development and implement of a Sentinel site reference monitoring program that Erica is going to talk about next. And finally, pulling in existing data sets from existing monitoring programs into our database to utilize existing data. And that's the end. Again, yeah, you can scan the QR code. It'll take you right to the website. And are there any questions?
We've got time. What questions do you have for Kevin?
Apparently it's clear as mud.
It is.
Yes.
Okay.
Anybody
Anything
online?
online? Not yet.
All right.
You just want to sit awkwardly and see if there's any questions that
Yeah.
pop up? Are you good?
I don't have to look at you. It's okay. Stand over here.
Here's the question.
I don't know if this is more for Kevin or Maddie, but what are like the sort of thoughts about how are estuaries going to be a priority for any of the upcoming integrated reports, and like what's the path forward for including their assessments in terms of like, you know, once we have these tools?
That is not a question for me. Any thoughts?
I don't know the answer either. I don't know, if Maddie, do you want to chime in? Yeah.
I really appreciate the talk. And I like how you outlined it so clearly with what's needed to get it to incorporation in the integrated report. I can't speak to the whole integrated report program's prioritization for bioassessment and estuaries necessarily, but I think the way you've outlined it really captures that, like, we want to assess all readily available data. So as long as the points we need to consider it readily available are met, and then me as one staff person, plus or minus whoever generously donates their time to help, has the, you know, time resource to incorporate it into our actual data processing and assessment timeline. Like those are kind of the limiting factors. So yeah, definitely a lot of interest. And the only reason I'm not asking you questions is because I have a very long list of them, like prepped to chat with you about later. So
Sounds good.
yeah, hopefully that provides a little bit of an answer, Rafi.
I would just add that we are developing online data support and kind of analysis tools that will kind of spit out some of the scoring that I've been talking about. I don't know if those are necessarily the scores that will be utilized for any kind of the integrated reporting, but we are developing online support so it's not just a huge pile of data that you have to work through, because we've done that for 5 years now and it's very onerous. So we're trying to code a lot of the work that we've been doing. So as more data come into the system, it can be spit back out and more easily digestible.
I'll do the online one. What are some of the outside data sources you are using?
Maybe data sets, is that what they're maybe external data sets? I guess I go with that. Folks down at SCORP are working with the National Estuarine Research Reserve to pull in their existing data from Tijuana and Penasquitos. We are working with the Monterey County Water Resources Agency on data they're collecting at the Salinas River, working with Elkhorn Slough to pull in information that's being collected with that Estuarine Research Reserve. And we're also working with the Morro Bay NEP to pull in some of their existing data sets into our database, in hopes that we don't have to implement all SOPs. If some of them are already being implemented at various estuaries, we can just utilize their data and kind of fill in the gaps with our protocols. Marco?
So you talked about how people can pick and choose which SOPs they want to follow, but is there like a minimum set that they should follow, or are there linkages? So like if you want to, you know, look at Necton, you have to do like these 3 parameters?
Yes, so that's where we come back to the table of everything. So if you're doing Necton habitat revision, see all the green squares for that row. Those are the indicators that you would want to be collecting for that individual function. And then we've developed kind of questions that go along with each of those individual squares that can then be rolled up and spit out kind of a function-based, I don't want to say report card because some people don't like the word report card, but score.
And so if you pull in like historic data that may only have 2 or 3 of those, then is that like a gap that you can't use that data then?
We would want to have overlapping time series. Yeah, as much as possible. Yeah.
Great, thanks.
Mm-hmm.
Great. Okay, we're at time. So thank you, Kevin.
Thanks, everyone.
All right. So for the second part 2 of the estuaries talk, Eric Stein is going to talk to us about the Sentinel site networks as a cornerstone of ambient estuary monitoring and assessment. And Dr. Eric Stein is the head of the biology department at the Southern California Coastal Water Research Project. Dr. Stein oversees a variety of projects related to in-stream and coastal water quality, ecohydrology, bioassessment, hydromod, watershed modeling, and assessment of wetlands and other aquatic resources. Oops, and we'll over to you.
Can you guys hear me now? All right, I'm gonna move around because everyone's gotta wake up. I might like walk up to you and like nudge you or something like that. Make sure you guys are awake. All right, so this is part 2, and so and thanks for the question, Rafi. Right, because our big goal, I'm gonna talk about sentinel sites, but I'm going to show you this slide because, right, you always hear you have to hear something 3 times for it to stick, right? So this is number 2, right? But our big goal in this, right, estuaries are important. That is the terminal receiving water of, pretty much all our watersheds. And so as we've been working with the MPA program, right, our goal is to really create capacity so that we can begin reporting on these in a regular basis and inform our management action. So we're going to sort of keep hammering this home until we have it in the integrated report, and then we'll stop showing you this slide, right? So, all right. So Kevin told you about the 3 questions, and so I'm showing you these again because if you think about these, are very analogous to the questions that we already sort of addressed through our freshwater bioassessment program, right? We have questions about condition, stress, and management. And so we have, as Kevin showed you, we have this framework, it's set up, it's ready to go, and so I'm going to talk about the next part of this framework. And so we have the monitoring plans and protocols, which Kevin talked about. I'm going to talk about the sentinel site element, right, which is an analog to reference sites, and I'll kind of unpackage that in a moment. And then Jill, when she comes after me, is going to start to talk about some of the assessment tools and how we start to take this data and move it into actual assessment tools that could be used in some sort of reporting. So you'll hear that more about that from Jill. All right, so here's our definition for sentinel sites. I'm not going to read it to you. That's why I put it in big letters so you can read it yourself. But I'm going to draw some contrasts about sentinel sites. Gets a little different than how we think about reference sites in the freshwater environment. And these are sites that are sort of designated for long-term monitoring over time because we want to use them to track trends over time. So I wanted to draw, most of you hopefully in this room are familiar with the RCMP program, the Reference Condition Management Program. That sort of is the backbone of what we do in the freshwater bioassessment program. And so very much like the RCMP program, in developing an approach to pick sentinel sites, we have, this is the flow chart that the RCMP program uses. We have an analog flow chart. I'm not going to show it to you because it'll make you all nauseous, but it's basically a kind of a similar process. But there are some important distinctions between what we do in sentinel sites and the RCMP program that I want to draw out. And this is largely due to some of the challenges in working in these coastal systems. So unlike the RCMP program, we include sites along a gradient of condition, and I'm going to show you a little bit more about this in the next slide. But that's largely because for the most part, almost all of our estuaries along the coast, the 500 or so that we have, are pretty modified already, right? That's kind of the nature of them being on the coast, whether it's because of direct modification or impacts from the watershed. So finding, quote, a reference or unimpacted site is very challenging. So we wanted to include sites along a gradient of condition to better understand those. And again, the key hallmark of the sentinel sites is that these are sites that are available for long-term monitoring. We can track them over time. We also include restoration. There's been a lot of restoration along the coast, so we have restoration sites that are part of the sentinel site network. So we can track trajectories of response, and then sites can change. They're not static, right? So they can move from one category to another over time. So those are some key distinctions. All right. So here's our 3 categories. Again, I've defined them, and I'm going to walk you through the selection process. So we have the sentinel site network. It's composed of reference, restoration, and then these other sites of interest that we might want to, again, track over time. So what I'm going to do is walk you through the process of kind of how we selected those sites, demonstrating how we've applied it in Southern California, although it could be applied anywhere in the state. All right. Maybe I just need to be closer. So here's our development process. I'm going to walk you through each of those steps. So as I mentioned, we have this gradient of condition, right, from degraded to least degraded. And so we do our reference sites are sort of at that upper end. I would sort of offer that very few, if any of the sites are, quote, sort of totally natural, right? So we have to find those least impacted sites. And then we have the restoration sites, which can span across that gradient or hopefully moving towards the less impacted site. And then we have these other sites of interest. So I'll walk through each of those. All right, so first we have to define our universe. So this is the definition of coastal tidal wetlands. And so I'm going to show you this in Southern California. So this is kind of the universe of sites we're looking at. And if we think about, Kevin said there's about 500 sites in the state, right? Depending if you're a lumper or a splitter and how you break them apart. In Southern California, we have 118 estuaries, right? I put this up a lot of times. People will go, huh, I only thought you had 5. But no, we have 118 of them. And they're in these different types of forms. So we have, as Kevin talked about, we have intermediate estuaries, we have small river mouth lagoons, we have more open embayments, so we have this kind of variety. And so we want to make sure that the Sentinel Site Network has representation across these different estuary types so that they're well represented within the Sentinel Site Network. All right, so we start by defining reference. And so the way we did this is we basically are looking at the system as a whole, as Kevin sort of talked about. We're looking not at sort of an individual habitat within, right? Because an estuary can have, mud flats, it can have tidal marshes, it can have subtidal habitat, tidal creeks. So we're looking at the system as a whole, so kind of this landscape scale approach in terms of the overall condition. And then we're trying to find within this kind of highly altered landscape, what are the kind of the best sites or the least impacted sites within the region that we can put into this reference category, right? And so we worked with our technical advisory team, our scientists team. And so for these coastal tidal systems, we identified, I guess, at least in Southern California, we identified these 6 elements. These are the things that we want to evaluate to determine whether these sites are in kind of their least impacted system, at least impacted state. And so we then have a definition for each of those. So this defines like what we think least impacted means for each of these 6 criteria. And then for each of them, I'm not going to go through all of them, but I'm going to show you the mouse data as an example. For each of them, we developed a scoring system, right? So this allows us now to collect data, whether it's GIS data or existing monitoring data, which Kevin talked about. Obviously, some best professional judgment. We have a science team that's well-versed in working in a lot of these systems. And so for each of those 6 conditions statements, we develop a scoring. So this tells you mouse state, right? And so it talks about the management of the mouse state. And so we have everything from 0, where it's hardened and highly impacted, to a 3, which is, other way, 0 to the 3 being no hardening or no impacts, right? So we have this kind of scoring system for each of those 6. So we can go through all those 118 estuaries that I showed you, and now we can score them, right, for each of those 6 indicators, and then we can develop an overall score to determine whether or not they should be in the reference category or not, right? So we went through that process. Wow, that got really big when it wasn't like that on my screen. So, all right, but the point is, you can see that we identified a subset of reference sites, right? So you can see we have some representation across our different estuary types, and so they're spread geographically through the region, and they're also kind of distributed across the different estuary types. So that's sort of the first step, is identifying those least impacted systems across the estuary types within the region. So once we have the reference sites, then the next one is we wanted to include some restoration sites. So the reason we wanted to include these is, again, if you think of our definition of sentinel sites, these are sites that can be monitored over time, and so we can continue to track them over time and understand the trajectory within the region. So we have criteria, again, up here, that what defines sort of a reference site that could be included in the Sentinel Site Network. So we looked at all of the restoration sites that are occurring in the region, and we looked at them relative to these criteria, and then we went through and picked a subset. And then we have this catch-all category, other sites of interest. And this is kind of where we want to be opportunistic, because again, the Sentinel Site Network is sites that we can follow over time. So these could be sites that are amenable because maybe they're in public ownership, maybe they're in a NER, maybe they've been acquired but they haven't been restored yet, right? So they're sites that we have the ability to follow over time. And so they can be sites that are maybe they're at risk, right? Because we know that there's some impending, threat to them, and they're being managed for that. So they're sort of a hodgepodge of sites that we have the ability to track over time. So when we put it all together, out of those 118 sites that were in the region, we've come up with 37 sites. So 14 are reference, 9 are restoration, and 14 are these other sites of interest, which could change designation over time. So that's our reference site network for Southern California, 37 sites. And through our BITE regional monitoring program that we manage in Southern California, we've had the opportunity through the last BITE cycle to look at all of these sites, right? So we're already collecting data at all of these sites, either through the BITE program or through some of those ancillary programs that Kevin mentioned, like the SONGS mitigation program. And so, as I mentioned, these sites can change over time, right? And so this little graph, this kind of conceptual graph shows that in theory, right, if you have a site and it's degraded, and then at some point it goes into the yellow category, that's a restoration site, right? We might be restoring it and putting a lot of money into restoring it. And hopefully, at some point, it becomes a reference site, right? Because we've restored it and it's in good condition. So these sites, they can change category over time, and so they're not sort of stuck in one category, but they still stay within the Sentinel site network. And so, again, I don't need to tell anybody in this room, there's lots of opportunity to use this. We can use it as a benchmark if we're looking at other sites and we want to compare, for example, the range, like that box and whisker plot. We can look at performance over time. We can track regional trends, right? And so there's lots of different ways we can use this Sentinel site network. And so the program that Kevin talked about, sort of the way the statewide monitoring program and the regional monitoring program set up, is that we have this kind of core monitoring that we want to do sort of once every 5 years. We have monitoring. Kevin talked about the fact that the monitoring we're trying to get it incorporated into permits and grant conditions, like the Coastal Commission and Coastal Conservancy, by using these protocols. So that's more ongoing. And then we have our special studies. But at the core, right, of the Venn diagram is these Sentinel sites. That's kind of the hub that holds everything together, is by being able to track these over time. And then when Jill comes up, she's going to start to talk about like how we can leverage this as we start to take that data and turn it into assessment tools, because as all of you know, sort of this backbone of reference and Sentinel site monitoring is really critical if you're going to have any sort of bioassessment program that you want to contextualize. So with that, we have a publication that talks about the process. I showed you the application in Southern California. We think that this process can be replicated in other regions across the state because the process is highly transferable. So it's been peer reviewed and published. And there's the QR code to our MPA site, the same one that Kevin showed you, so you can get all of the publications and all the other good stuff. And with that, I think I have time for questions. Wow, look at that. Questions? Ethan.
Hi, thanks, Eric. I was wondering how you determine like what proportion of sites you put into each designation, like reference or your other categories, and if they're allowed to change designation over time, are you going to need to then go back and fill in those categories as things move in and out?
Right. Yeah, good question. So the question is about the distribution of sites into the reference, restoration, and other. So we didn't sort of a priori have sort of a predetermined number, but we had a goal to have somewhat of a balance, right? And so it's not like they have to be completely even. And like any network, we see this as kind of a living resource. So because sites can change designation. So if in a perfect world, right, we'd start to get more sites in the reference category, right? And so it's conceivable that if we've restored all the systems, there might, no longer be anything in that restoration category, that conceptually, right? That could happen with lots of money and time. But the idea is that we, revisit the network over time. So as sites are moving, right, they can kind of go one way or the other. It could be reference, and then they could kind of fall out of reference condition over time, or restoration sites could move up. So it's we envision it being dynamic, and so that the designation can change as we continue to monitor these sites over time.
Thanks.
Eric, great presentation. I'm curious, when you're talking about them changing categories across that gradient, if you've got a site that's of other interest and then it gets restored, you mentioned it could potentially move up to the reference category.
Mhm.
Now, I don't know what your cutoff is for something considered as a reference, but you can restore an estuary, but you still got the upstream watershed that potentially isn't restored, that's draining down into that estuary. So how's it going to move up to the restoration? Are you considering upstream sources as part of your minimally influenced?
Yes, so this is a great question, so I'll go back. So we had these, oops, there you go. Too far. Okay, so these are, so you can see watershed stressors is one of those, right? And so these are the criteria. So as we look at these sites, because again, we're trying to track them over time to create these long time series. So we're looking at all of these and evaluating the estuary relative to kind of those statements. And so I showed you that little scale for mouth condition. So we have one of those scales for each of these 6 criteria. And so when we look at a site, watershed stressors is one of them, right? And so, of course, none of these have absence, right? So it's all a relative scaling, right? Because these are all in sort of impacted watersheds, right? So when we go through that scoring and we assign scores for each of those and we kind of roll them up and we sort of took the upper sort of quartile of those scores and those became our reference sites. So as we continue to follow these sites over time, if they're scored and they get into that sort of upper quartile, then we would call them reference and change their designation that way. Does that make sense?
Yeah, I guess so. I'll talk with you afterwards.
Okay, okay.
Hi, Eric. Thanks for the talk. It was great as always. You're a fantastic presenter. Just some thoughts about reference sites and best observed versus truly reference. I mean, if San Quintin itself is also degraded by
Right.
different stressors than
Yep.
Southern California. And I guess that also applies to our freshwater reference sites as well. It's best observed. But I was just kind of thinking about pitfalls or expectations associated with what might be a theoretical true relevance reference relative to best observed.
Yeah, so, right, this is so it could be a long conversation, right? So right, there's been lots and lots of, the question has to do with this idea of best observed versus kind of true reference or kind of what you might call unaltered, right? So that's what the question is about. Obviously, this has been kind of a debate in the literature and in our community for forever, right? As long as I've been doing this, right? Is how do we define reference and kind of that. So there's, right, the famous Stoddard et al. Paper, right, which talks about the different types of reference, right? And so for the estuaries, we could go back and like look at our historical ecology studies, for example, and we can kind of infer what that least altered condition. But even then, right, that's sort of circa 1850. We know that these systems have been highly modified by humans for hundreds and hundreds of years. And so kind of philosophically, because we want this, or I guess I should say sort of more practically is probably the best way to say it, we want a set of sites that we can monitor moving forward into the future and use them to contextualize all the management actions that we're doing, right? And so if we have this kind of hypothetical least altered, it's important to understand that, but it's probably not the best way to contextualize the management actions that we're currently doing, working in this kind of highly altered landscape that we live in. And so that's why we chose to try to anchor this with kind of the best observed or the best available in kind of the Stoddard terminology, the best available that we have, because it provides a more useful context when we're thinking about management actions or targets for restoration versus, say, historical optimum that we probably won't be able to reach because the landscape's been so highly altered. But definitely a healthy philosophical debate that we probably won't solve in this room. So.
No time, Chad. We're getting into Jill's time, so maybe you
Okay.
guys can chat over the break.
Okay.
All right, thank you, Eric. All right, so the third part of the Estuary bioassessment talk is going to be presented by Jill, and she's going to be talking about eelgrass bioassessment as a potential bioindicator of estuarine health. And I should have asked how to pronounce your last name before we. Tupitza. Okay, so Dr. Jill Tupitza is a benthic ecologist with expertise in bioassessment and community response to change. She specializes in using benthic macroinvertebrates to infer local ecological health, community dynamics, and food web interactions. And feel free to use that or the clicker. And you're on, you clicked a button.
Thank you,
Okay, good.
Allie.
Yeah.
Oh, awesome. Thanks, Erica. Okay, good morning, everyone, and thank you so much for your attention. I'm really glad to be part 3 of 3 of estuaries. This is part 3 of 3 in a series about estuaries, and you've probably seen this slide before. We're really hammering this point home. And we're here to make this point that estuaries often get neglected in reporting, in particular the state's integrated report, because of a lack of tools, monitoring framework, and protocols that are both scientifically sound as well as used widely and available. And so in estuaries, there are a number of candidate bioindicators that could be used for a bioassessment tool in stream and nearshore environments as well, but in particular estuaries. You all are probably very familiar with ways to do this with fish, plants, algae, benthic macroinvertebrates, my favorite. And all of these candidate indicators are useful to us because they're responsive to stress and management action within the context of their environment. But today I'm going to talk about eelgrass, submerged aquatic vegetation, but specifically eelgrass. And what I'd like to share with you are the fruits from our first round of monitoring and development of an assessment tool based on ecosystem function to try to quantify and put some numbers to how eelgrass beds function and what they mean about estuaries. So in case your background is in streams, which I've noted from a lot of the talks in the past couple of days, you might not encounter this type of vegetation very often. So here's just a little quick refresher. Eelgrass, or Zostera, is a genera of perennial flowering vascular plants that live in brackish to full saline conditions. And this type of aquatic vegetation is characteristic in a lot of California's estuaries and embayments. And they provide also essential ecosystem functions to those estuaries that are not redundant in other systems. So for example, provisioning of nursery habitat. If you remove the eelgrass, there are no other subhabitats that really come in and fill that role. So that's why they're important and that's why we can use them. And you've heard a lot about developing a monitoring framework from Kevin and all that goes into that, all of those protocols, all those people on board that need to be in agreement. And you've heard about reference sites and selecting sentinel sites and how that's done from Eric. But I'm really here to talk to you about where the rubber meets the road, or in the context of this group, where the salmon meets the beaver dam analog, which is your bioassessment toolkit. How do you actually put this into action? So I'd like to walk you through an example about how we've used eelgrass to create a scoring tool to kind of understand these questions in estuaries. So we have created an eelgrass-specific assessment framework. Well, it's designed for SAV, but it's sort of also designed to be agnostic to species and habitat, so you could use it for something else. But we've decided to use it for eelgrass in this particular case. And this might be familiar to you because it sort of reflects the same type of 3-tiered assessment framework used by the EPA to assess ecosystem function in general. So I'll walk you through it. On the left, Tier 1 kind of covers the question of extent in terms of present extent and habitat suitability. It's had the most progress to date. Tier 2 kind of looks at the health of the plant of eelgrass itself. And the third tier, which is where I'm starting this concentrated effort, and I'd like to share with you what came out of it, gets to the question of condition through the lens of ecosystem function and seeks to build a tool to better understand the condition of these habitats. So we've got a couple of projects that are underway that address that third tier. And the first one was to conduct a literature review to propose a conceptual model that links these structural metrics that are measurable within eelgrass to how they actually function in estuaries. And the idea behind this bioassessment tool at its core is to use the structure of eelgrass to estimate ecosystem function. So through this literature review, We went over a lot of literature that link those structural metrics that you can measure in the field, such as percent cover, shoot density, and things that you can measure in the lab from taking a sample, such as above and below ground biomass, and linking that to the actual ecosystem function of eelgrass. And this is generally the suite of ecosystem functions that eelgrass is responsible for in estuaries. And our review explored the relationships between the structural metrics and these ecosystem functions. So let's take a quick look at the results. This is a little bit of an overwhelming table. I'm sure you've had enough of these today. So I'll point your attention to just the rows here, which contain different measurable structural metrics, including above and below ground biomass. These are the things that we know how to measure. We have protocols for this. We're mostly in agreement. And the columns contain ecosystem functions, which is what we're interested in estimating. But we can't just go out into the field and measure these things and get a sense of them. And so the colored boxes indicate whether or not that metric relates to that function. So for every blue box that you see here, there's a piece of literature or a body of literature that describes the relationship between that structural metric and the function that it produces. So for example, shoot height has a strong relationship with nectin habitat based on literature. In general, the higher the shoot, the more habitat is created. So to calculate the overall condition of an eelgrass bed, it's recommended that you use all 7 of those ecosystem functions. But for the sake of simplicity, let's just zoom into one of those ecosystem functions and unpack how the scoring tool that comes next works. So nectin habitat is estimated using 7 different eelgrass structural metrics, which are shown at this table. So the next step in our plan was to actually go into the field or build a team to go out into the field so that we can measure this, get a data set large enough so that we can estimate nectin habitat confidently. So we worked with our regional partners, many of who are sitting in this room, to collect structural metrics data from about 56 sites with eelgrass beds with the ultimate goal of building an assessment tool based on ecosystem function. So we worked with a team of eelgrass experts and motivated managers to collect all this data in the spring of 2023 and fall of 2024 via the BITE Regional Monitoring Program, with SCORP sort of facilitating and everybody playing their role. So to estimate nectin habitat function, we endeavored to collect all 7 of these metrics. It's probably best if you have all 7 of the metrics, but in reality, we were able to go out and collect 4. So let's walk through how the scoring tool works with real data that we are able to collect. Here on these box plots show the 4 structural metrics that relate to nectin habitat function that were collected in the field and made its way through the data portal back to us. So these box plots show the whole regional data set for all of these measurements. So for example, the median shoot height in the Southern California Bight is around 40 centimeters. If you take nothing else away today, a little fact. So from that, each of these box plots, the data is split into quartiles based on the rank order. So here shows the roughly colored areas you see here show the different quartiles based on rank order 1, 2, 3, and 4. So that's how we take our raw values that were measured in the field and convert them into something that works well with each other. So for example, let's say we sent a dive team out to an eelgrass bed and recorded the structural metrics from an eelgrass bed. They went out to collect shoot height, shoot density, percent cover, took a sample back to the lab, and measured leaf area. The peak lines represent measurements at one single bed and where they fall within the data set. And so those individual data points are then binned into those quartiles depending on where they fell within the regional data set. And so the green numbers represent, they can convert something like 40 centimeters into quartile number 4. So the next step is to average those quartile scores into an overall function for nectin habitat. And here the orange dot shows the average quartile score for nectin habitat. So here's some real data. For the whole regional data set of 56 eelgrass beds, these are the scores for nectin habitat function specifically. So you can see in the green, we've got good condition. We've got a number of sites that were classified into good condition overall. In terms of nectin habitat, a few that were pretty poor, and most of them ended up at a moderate condition. So shown another way, this is the geographic representation of nectin habitat function through the whole Southern California Bight. And the orange triangles show moderate condition, which is where most of them ended up. And unfortunately, my table got cut off, but I believe that's a 6 that were put into poor condition based on my memory. So this new scoring tool can be used for bioassessment of eelgrass and refined in future surveys. So I want you to think about this as more of a scoring tool set with its default settings. So we want to use future data sets to sort of refine what we know about this. So we can also dig into this, the differences in ecosystem functions based on location. We can use the tool to list locations where ecosystem function is in good condition. On the map at the left shows a few key points around the area of San Diego where ecosystem functions were listed as good and which specific ecosystem functions were listed as good. So if you're interested in a particular area, you can build a figure in a map that will show you these things. Moreover, these are the functions in the same area that got listed as impaired. So if you're interested in a particular bed, you can kind of dive in and take a look at that. So we can use this in a number of ways. Managers can easily look at which functions are impaired in their specific area and prioritize restoration and management action. Moreover, we can use this to look at eelgrass beds through the lens of ecosystem function over time and with or without management intervention. So I present to you today the first iteration of this function-based tool, which can be used to score eelgrass beds and try to help us fill in the gaps about how we understand estuaries and how we can attach numbers in reporting. At this point, the tool is a proof of concept, and we need to refine it in the future in a couple of ways. So I'd like to highlight a few of our next anticipated steps and goals and kind of open the door to collaboration if anybody wants to join us. Oh, sorry, I got a warning on this computer. Okay. So the number one thing we need is additional seasons of data in different habitats. And right now we've got a lot of data in the Southern California bight, but we would love to expand up the coast where eelgrass is also found. The more data we can use to sort of refine this tool, the better representation it will give through the region and through the state and outside the state, maybe. We also need to independently validate all of those structure to function relationships. So all of those blue boxes that I showed earlier on the conceptual model, all of those need independent data sets to validate that the structural metric does in fact relate to the function. And that through that sort of exploration, we can understand with a more nuanced way how we can further refine our tool. And we can also use this to combine all the 7 metrics together in ways that are reflective of the ecosystem. So with that, I will take questions. And I don't.
That was excellent. Thank you. Oh, I'm loud. How did your good eelgrass bed sites align with Eric's Sentinel reference sites? Did you have good sites where you thought you also had reference sites? Have you looked at that yet?
Excellent question, and we have not explored that yet, but certainly will. I do know that there were a number of sites that a lot of this was done with a probabilistic random sampling design, but a few of these sites were targeted for what was thought to be good conditions. So we could go back and look at that, and I think that will be an excellent next step.
Very cool, thank you. Since both you and Kevin mentioned the integrated report, now or in a long chat later, I would love to get your pitch for connecting indicators like eelgrass to the 303D list, which is really bound to be pollutant focused. So I want to use as much readily available data as possible, and I think it's very valuable. And of course, these indicators are indicating us to potential pollutant problems. We want to consider that. It just gets a little bit tricky to incorporate into such a pollutant targeted program. So I would love to use your knowledge and Kevin's knowledge to get your ideas. I also think there could be an interesting, unrelated to the integrated report, I think this type of indicator and data could be really, really useful to CDFW's oil spill prevention program. Their field responders create like preliminary area response plans that say like when there's an oil spill in Richardson Bay or whatever, like this is exactly the type of equipment we need to set up, areas to prioritize. And I think knowing healthy eelgrass beds could really target those efforts and be cool.
Amazing. Let's chat later. Would love to brainstorm some ideas for how we can get this off the ground and use it in productive ways.
I'm gonna bring one in from online. Has your tool been used by other organizations yet? It could be used by restoration ecologists.
Our tool is hot off the press. We haven't even published on it yet. We have a technical report due, or the BITE overall report is due in March. So we'll have it sort of out and available to the public by that point in time. We also anticipate having, well, we do have a working data portal, but we're also going to have a public-facing site that has all of our protocols and our work and field plans, as well as the data for retrieval and everything. So it will be available to be used, but no, nobody's used it yet. You all are the first to really hear of it.
Jill, hi. Have you considered pulling in, is it possible to pull in data from other monitoring programs, or do they have to, are there specific protocols within your effort that aren't, I'm thinking of like the Morro Bay NEP and the Elkhorn Slough NER. They both have extensive eelgrass monitoring programs, but I don't know if their protocols specifically align with what you developed. Is there a way of pulling in their data to pull in at least 2 additional sites that may be helpful?
I would have to see those data and how well they align with the protocols, but given that it was developed by a lot of the protocols themselves were developed by eelgrass experts in the area and people with a lot of experience, I imagine we're overlapping with a lot of the same folks. So that's definitely possible that we could pull something like that in for additional sites. Yay, 2 more sites. Great.
Hi, thank you to all 3 of you for your presentations on the estuary bioassessment. And something I've just been thinking about during this past hour of the presentations is how these reference sites and these like using these bioindicators. I'm not an estuary biologist, but how can we be sure that like California is so diverse? How can we lump it all together into one cohesive like assessment when like the southern is so different from the north, and if maybe eelgrass is more productive in the south, then would we be thinking that maybe northern eelgrass beds are like less productive, but they're actually really good for where they are, but we're using, across the state as reference sites? If that's making sense, like how can we capture those regional differences in a statewide bioassessment?
Yes, I think you're asking exactly the right questions, and that's sort of the track that a lot of our minds are focused on. Is absolutely, eelgrass is different in other regions, and right now what we have is a pretty reasonable starting point of a scoring tool that's specific only to Southern California. But you're right, eelgrass is very different. That's why we want to pull in different data sets and experts to kind of understand, not just trying to shove it into this scoring tool and assume that it's going to work, but use it as a learning experience for how we need to change the tool to accommodate for things like, I know that the amount of intertidal eelgrass is a lot higher in the North Coast than it is in the South Coast. That probably manifests itself through different structural metrics in a way. So yeah, basically what I'm getting at is like, we're absolutely like right there and we're thinking about these things, but that's something that needs to be included in future iterations of bioassessment tools.
Thank you, Jill. Oh, right bag for you. You're welcome. Okay, and thank you all. That was an excellent session. We are at break time. So a couple announcements before you part. There's a feedback survey here. So if you can pull out your phones at some point and scan that, we'd love your feedback. We're also looking for a laptop charger. This is gonna be real hard because they all look the same, but someone picked up, I think they got swapped at some point. So if you think that might be you, come talk to me and we'll hopefully swap that out with Melissa. I don't know if she's in the room right now. If you don't know what I'm talking about, fine. And Melissa's in the back, so this is where the laptop charger mishap happened, I think. So, and then the other announcement I was gonna make is just a reminder again that we're 20 minutes ahead, right? So we're gonna end at 12 o'clock for lunch. There should be snacks and coffee out on the table by now too, so break time. See you all back soon.
Okay, so we're going to start off with Dana Garcia from California State University, Bakersfield. Oh, so sorry.
All right. Hello, everybody. My name is Dana Garcia, and I'm from an undergraduate student from California State, Bakersfield. So today I'm going to be presenting on tracking trash patterns of anthropogenic litter in the Kern River, and this project was done through the guidance of Dr. Ray McNish, who presented yesterday. Oh. Wait, I think I got this up. Oh, it took me. Oh, okay. Get you back. Right. So anthropogenic pollution, fresh water, as you know, is a rare and limited resource. It's a variety of pollutants enter our fresh water, which degrades freshwater degradation and includes things like bottles and bags, fertilizers, and pesticides, which enter our fresh waters through illegal dumping, as well as industrial waste, wind transportation, and stormwater. Anthropogenic litter, also known as human trash, includes plastics, processed metals, wood products such as lumber, and synthetic rubbers. It is dangerous for aquatic and terrestrial life. This is because it causes entanglement, it degrades their habitats, and it disrupts their food webs. Anthropogenic litter also impacts human life. As we know, plastics break down into microplastics, which later we consume through our own food. For river ecosystems, river plays an important role by transporting water nutrients. They provide habitat and support biodiversity, and we use it for drinking water, farming, and energy. The breed dams, one key feature is that they trap organic matter and man-made materials in river streams. That is a picture of what a debris dam is supposed to look like. And rivers also often serve as a conduit for the transfer of anthropogenic litter into our environment. This brings me to my research question: how do river habitats and anthropogenic road bridges impact the distribution and abundance of anthropogenic litter in rivers? For my first prediction, I thought the anthropogenic litter community will be dominated by plastic items across sites and habitats. For my second prediction, I said most anthropogenic litter will be abundant in the breed dams, with the breed dams also capturing more flexible items. For this project, the Kern River was used. The Kern River ranks as the 10th largest river in California. It is widely recognized for its strong currents and natural beauty. It is a popular site for recreation activities such as fishing, kayaking, camping, and as well as swimming. We focused on the lower Kern River, which flows through Bakersfield, California, and crosses by 13 road bridges. These were my 4 study sites in the lower Kern River, which were used to collect litter data. And the bridges also provide informal shelter for the local and house population. For methods, transects were set up 5 meters along the length of the river and span width of the rivers upstream and downstream of the road bridges. And these were like 3 transects that were set up. For under the bridges, we had 5 paired debris dams and non-debris dams that were identified and measured along the bridge's piers. After all of the items were collected, they were brought back to the lab and they were cleaned, air dried, categorized, and measured. These were my preliminary results are from summer 2025, when the lower Kern River was predominantly a dry riverbed. For my first preliminary results, we have material relative abundance across bridge sites. It goes from downstream to upstream, in which we see that plastic is overall the most abundant, and paper and cardboard follows a close second. For the Callaway site, we do see that there is a standout for by styrofoam, and overall these results did show that there was a significant difference. For my second preliminary results, we have material relative abundance across habitats, in which we see again that material abundance is still consistent with plastic, and overall we see that in the non-debris area we have more diversity, and these results did show there was a significant figure. For rigidity relative abundance, there was a study that was done a couple years ago in which there was found more flexible items overall, but in these results we did find more rigid items, and even though we did see more rigid items, our results did show that there was no significant difference. For fourth preliminary results, we have mean anthropogenic litter mass across habitats for each site. For Allen, upstream had a higher mass. For Callaway, we see downstream and upstream had a higher mass as well. And for Mohawk, we see that downstream had a higher mass. This is probably because it is the largest bridge. And for Stockdale, we noticed that upstream has a higher mass. And for these results, there was a significant difference for both site and habitat, but there was no interaction between the two, which means that habitat did have habitat effect was consistent across all of the sites. For discussion, plastic is most abundant because it's common, it's durable, and it's easily transported. Rigid items were more common than expected, and flexible items move via wind and human collection. And this study will continue to observe litter transportation and accumulation when the river flows again, which it already does. Right. Any questions?
Hi, this is great. So we just started kind of doing the same thing, like kind of categorizing the trash when we do our pickup, like our cleaning. And one of the things that we kind of were attributing to, again, we're also at a smaller scale, we're on the reservation. So there's like land use or like specific trash that's associated to different things in that area. So like, let's say if we see a lot of like wrappers or candy trash or like, cups, we know that it's like down the street or like down the street from the gas station, right? Just wondering if that's anything that you are going to eventually look at, like what could be contributing to the different types of trash you're discovering in that area. I guess it's floating down. We
Yeah.
just also put booms up on our creek to just kind of see what is coming down. Just wondering what's like the future.
So for these 4 bridge sites, there's really a lot of space in between where like the river does like flow. So I don't think anything like the gas station you said might, but there's a lot of on local and house living there, and a lot of wind transportation does happen as well. So yeah, that's something that we probably would look into as well though.
Are there types of litter that you think are more or less environmentally harmful?
More or less. Well, plastic is overall very harmful. There's a lot of toxins in it, as well as styrofoam. They all break down, which just degrades like habitats, and obviously all of the animals are consuming it. So yeah, I think most of anthropogenic litter is gonna be just harmful overall.
Thanks.
This is sort of like some of the early studies they did in '86, looking at sources for down in Fresno, the sources of things they did, areas, commercial, industrial, and double. I also worked on outfalls in the Santa Clara Valley, looking at the trash and what was coming in. And so all you're doing, it seems to be, is looking at the tail end of the dump sites from the surrounding areas. All you're looking at is the toxicity. Are you looking at any of the drainage areas that are coming into your sites?
Currently, no, but that's maybe something that we could probably consider as well to do.
Yeah. Okay.
Thank you, guys.
Okay, next up we have Andres Aguilar from California State University, Stanislaus.
And then to move, I just press the right key. Okay. Get this on. Ooh. Oh, show some slides. All right, perfect. Hello, everybody, and good morning. My name is Andres Aguilar. I am a first-year master's student at CSU Stanislaus, and my advisor for this project was Dr. Matthew Cover. And we were looking at how this interesting stonefly is able to fit its life into a 10-week stream. So to get into it, I know a lot of us already know the difference between perennial and intermittent streams, but I just wanted to include this anyways. But usually when you're talking about stoneflies, more often than not, you're probably thinking cold, perennial streams where they can really, thrive. But in this situation, in Corral Hollow Creek, it's an intermittent creek here in the Diablo Mountain Range, so just west of us. And the creek was able to hold water for about 70 days. So to kind of further this point about stoneflies being able to live in intermittent creeks, there was this really interesting study done by Bogan and Carlson in 2018 where they went out to Pinnacles National Park and tried to identify these stoneflies that were living in these intermittent streams. And of the 14 that they were able to find, 13 were found in temporary streams or intermittent streams. And of those 13, 3 of them are part of the Mesocapnia species, which is a perfect segue into our study species, Mesocapnia bulbosa. The reason this species was brought up was because it's a fairly young species, first described in 1990 by Nelson and Bauman. It is important to note that in this study that I include, only the adult males were described, so no females or larvae were described. But this kind of furthers the point of the large knowledge gap in the life history of Mesocapnia bulbosa. And because of this knowledge gap, we were able to come to two outcomes that we wanted to figure out in this study. Was we wanted to describe the life history of Mesocapnia bulbosa and document the larval stages as best as we could. And then because of this and because of previous aquatic invertebrate studies, we ended up coming up with 2 sort of conflicting hypotheses. The first one being rapid development, so that we would see rapid development within that 70-day stream cycle. And then that we would see semivoltine life cycle characteristics with some sort of diapause later on. So then, in order to answer these questions or look further into this, we had weekly site visits during that 70-day stream flow, spanning from February to March, February, April, and then we collected our samples, brought them back to the lab, and measured the larval head capsule and the prothorax capsules to paint a better picture for us. So what did we end up finding? So we found that the head and prothorax capsules ended up growing pretty consistently. And in the earlier stage of the intermittent stream, much of the surveyed population had similar sizes. But then as the weeks went on, we started to see this jump in asynchronous growth. So some individuals were growing a lot faster than others. And then towards the tail end of the stream's life cycle, we started to see occurrences of smaller, more freshly hatched individuals. And this was, fairly interesting. And we were able to find another paper by Bogan that was published in 2017, where they were looking at Mesocapnia arizonensis that ended up, what that species would do was undergo larval diapause. So the larvae would, dig down into the stream bed and wait for the next flow cycle to occur. We think that's what's happening in this situation, but more research is definitely needed to solidify that point, which is
eventually what we want to do. I'm going to skip this slide just because I'm going to skip it. But why does this tiny stonefly matter? So intermittent streams support really unique fauna because of that shortened time frame. And most of that unique fauna has a pretty flexible life cycle because of that shortened time frame. But it also is kind of a testament to the adaptation that these species have had to grow and develop in the face of climate change, especially with the more intense and severe droughts that California has seen over the past quarter century. And all this information is eventually going to help us with creating management or conservation strategies and plans, especially for the Mount Diablo range. There's a lot of unknowns in this mountain range, so if we can get some more information about Mesocapnia babosa, we can move forward in implementing best management practices. So lastly, I wanted to reiterate some of the closing thoughts. Short streams, so intermittent streams force fast life cycles. I do suggest that a multi-year study be done to better understand what type of diapause these invertebrates are leaning on to survive. And yeah, if anybody has any questions, there's my email, and then I'll be up here for questions. So thank you very much.
Very nice presentation.
Thank you.
In your dissertation, will you propose or request future research to try to track down where these individuals are or eggs, where they're diaposing, and if so, how?
Yeah, totally. That's a real tough question to wrestle with, right? How do we go about studying that? But yeah, I do think that it's super important to try to figure out where they're doing it, how they're doing it. Yeah, perfect. I have to consult with my advisor further about it. I'm fairly new to the invertebrate game. My personal thesis is going to be, or at least right now, it's about California tiger salamanders. But Dr. Kober ended up allowing me to segue and learn more about stoneflies. So I'm still wrestling with some of the new information, and I'd love to hear some insights from anybody who's big into the invertebrates. But yeah.
So I happen to be studying stoneflies from non-perennial streams also.
Perfect.
And I have a hint for you. That stream bed looks pretty penetratable, like you could dig with a pick, possibly, or set wells. And hyporheic stoneflies have been collected from wells well far away from the stream in other studies. And that might be where you find these larvae diaposing.
In the wells?
Yes.
Oh man, I should have brought my pen up here. I have my notebook.
No.
I would have noted this down.
I'll give you my number and I'll.
Yeah, perfect. Yeah, perfect. Oh, cool. Thank you. I really appreciate that. Are there any other questions or anything? Or suggestions? I'm still learning about stoneflies, so this would be really cool to tap into some of the knowledge out there.
And we know Matt. He's pretty cool.
Matt's a pretty cool guy. If you don't know Matt, you should know him. He's a pretty cool cat. I think he's watching. Hi, Mom. I think she's watching too. But yeah, perfect.
I'm curious for this particular stream, how much you know about the flow regime for the year you sampled. Is 70 days typical? Was it I didn't catch what year it was. So was it a drought year?
Yeah. It was this spring. I should have mentioned that. So my apologies. Let me see if I go back to the images. It's right here. I think we first started seeing water. I think I have this noted sometime in late or mid-February. I'm not too familiar what the flow regime is, but that's why part of that multi-year study we'd be able to get a better picture of what that is, because it's super important when understanding how these stoneflies are, reacting to their environment.
Yeah, I think it would be interesting to see wet versus dry years, how the life history might play out.
Yeah, totally. I agree. No, online question.
Okay, several online questions.
Wonderful.
Can you explain how this research work can help benefit biological life in the Diablo Valley area?
How it could benefit biological life or biological understanding? Because biological life, I mean, we can continue to preserve the species because it has a limited range. I think I have a map up here. I think there's only about 7 streams in Diablo range that this species is. Yeah, it's highly limited, so it's pretty constrained. So if we can go about protecting those environments, or at least that area where these streams are, then we can help conserve that, the Mesocapnia babosa. I think I answered that. I don't know if that answers the question. Yeah? Okay, perfect.
These two should hopefully be similarly short, but what was the collection method used for these stoneflies?
Okay, perfect. Yeah, I should have explained that too. The collection methods were, we took a bunch of undergraduates out there and we gave them dip nets, or the D dip nets. And we went and just collected as many individuals as we can in riffle environments where the riffles are.
Thank you. Okay, last one. Do you have guidance for monitoring protocols to not deplete this species or other specialized species populations? Few streams, small populations.
Yeah. Unfortunately, I don't have any insights on that. I'm still fairly new to the game, but hopefully within the next year or two, I can answer that question fairly confidently.
Cool, thank you.
Yeah, cool. Thank you very much, everybody.
Okay. Okay, next up we have Alexandra Yokomizo from University of California, Davis, and Restore the Delta.
Is it on now? Okay, sorry about that. So for this project, it was particularly part of my practicum for my Master's of Science in Environmental Policy and Management at UC Davis. So what that means is basically I had to do an internship with Restore the Delta, and then I was able to create any deliverables of my choice. So I chose to do science. So as part of my internship, I was hired as a climate water advocate. I was then tasked with helping the HABs testing, and then all of the maps and graphs, that's specifically what I created. So for Restore the Delta, they do harmful algal bloom testing. They do it in collaboration with the Central Valley Water Board and California State Water Resources Board. They've done it since 2022, and they test usually from beginning of May all the way into September. Every week, they test the same 7 sites and collecting a bunch of different data. That data includes both environmental data along with actual water samples that they're able to take back to their lab, which then they run tests on. The test that they do is specifically a recreational water Abraxas microcystis test, and then whatever data comes from that, along with the environmental data, is then shared with the state. Okay, so one of the main things that I wanted to look at for harmful algal blooms was the detection. So the 2 years that they actually found detections was 2022 and 2025. And so the way that I've chosen to illustrate that today is on different maps. I hope you can see them, they're kind of tiny. But they have the 7 different sites that, that Restore the Delta takes data from. You're able to see the different legends that shows you the scaling of the different number of detections that were actually found at each of the sites throughout the years. And then you can also compare them side to side. One of the other things that we looked at were different drivers for harmful algal blooms, specifically salinity and different temperatures, specifically water temperature and air temperature. So salinity, we were able to compare all 4 years, specifically the variance of salinity at each site, because it's not very helpful if you compare the different sites because the different sites are going to be all different. So with this map that I made, you're able to look at the variance for each site throughout the different years. Similarly to the temperature for both water and air, you can do the exact same things. You have the legends that show the different levels which they're expressed in, and the different colors too. So the way that I chose to do this particular type of communication was specifically through ArcGIS story maps. So all of the graphs that you've seen today, the graphs and the maps are on an ArcGIS story map that I created. It's basically like a website that you can go and have narration going along with the different graphs and maps that I created, mainly so then the public can actually know what they're looking at, because a lot of times when we're talking about HABs To the public, they don't even know what HABs are. So for part of my website, you can actually see like, what are HABs? Why are they in Stockton? Why do we care? The Stockton area is part of the estuary. Why is that important? So it allows people to actually understand what they're looking at instead of just like removing that scientific barrier. So then people can have access to that information. And so they can see the same information that we see in terms of detection and also comparing the different temperatures, but in just a way that is accessible. Okay, so for this, again, this is only one way that you can disseminate information. I thought this was an easy way that allows people to truly understand what's going along with this science, so that it's known and people specifically for HABs know when to stay away from certain water like areas, and so they don't recreate or even take fish, because that can be super harmful, especially if they ingest the fish, or if the bloom is bad enough where they can gets aerated and into their lungs. You'll notice that I didn't really make any conclusions for this data, mainly because I did this data over pretty much the summer, and then the conclusions and all of this data that I made was mainly over a month. So my time frame was very short, and it's really just to give an explanation of past and present data in an easy way, and that was the main point of this. I have a little picture below, and if you ask me, I will give you the website to actually access this information, because it does go into a lot more depth than I have just for today. So you can actually see all the graphs that I've created and the different maps. Please look at them. I spent many hours, and it's like 500 different like collections with a bunch of different variables. Yeah, these are my acknowledgements and different citations. Thanks for listening.
So I guess I was just wondering, did you test it with like a community group to see if that was a good way to display the data? Or do you have a target group that you're trying to communicate to?
Yeah, so I haven't actually tested it because I created this not that long ago. But where it's going to be hosted is actually on the Restore the Delta website, and they will also make a printout of some of this information. So when they go to community outreach events, they can actually hand people that data at the same time.
Sometimes it's really difficult to communicate the science to communities, and so just that's all.
Thanks. As somebody who actually works for a community science organization, and I'm in the process of trying to build a story map for our like 30-year long-term data set, something that I've run into issues with is, the amount of data you can reasonably show on story maps before it completely dies. I'm curious, is there a plan in this for taking what you've done in the longer term and making sure that it is usable, beyond the 2 years of data that exist right now, or kind of like thoughts on how you can add more data before or without like overloading it?
Right now, so this data actually covers 2022 all the way to 2025. So it's all 4 years. In terms of overloading, I don't really have a plan, because I use this just to restore the deltas data. If you wanted to do it in a different way, I think you could do it still with ArcGIS and story maps. The way that I kind of got around that barrier of having to show a lot is just you can do different slideshows and just have them right next to each other. Sometimes the processing data, especially for story maps, can be hard, and the way that I also got around that was just manually breaking everything apart into different Excel sheets by myself. I don't know if I recommend that, but that's the way I did it.
Thank you.
Any more questions? No? Okay, thank you again for all of our Student Lightning Talk speakers.
And while Alexandra's walking away, if you brought cash for the R workshop, and you have your suggested donation for that workshop, find Alexandra and she'll be taking those. But she has to leave at lunch, so I'd say find her at the break. Thanks. Yes. Here, you want to say it?
Where should we meet before we go upstairs?
Okay, gotcha. And then for folks that are gonna do the SAFIT workshop, we'll meet in the lobby area on the first floor where you signed in, and then we'll at about 1:15 or so. Yeah.
Now Now we are transitioning back into our longer talks, and Daniel Pickard is first up. Dan has a master's degree from the University of Alabama. He leads the Aquatic Bioassessment Lab at CSU Chico. And today Dan will be sharing information on macroinvertebrate assemblages, riverine wetland conditions, and physical habitat conditions on Santa Rosa Island and Channel Islands National Park. And he's also a Niner fan, like myself. Go Niners.
Good. Okay, great, everyone. Thanks for being here again. We're gonna switch it up a little bit now and start talking about islands. Santa Rosa Island is part of Channel Islands National Park. This study was done as part of the National Park Service Inventory and Monitoring Program. And it's a collaboration between Channel Islands National Park, CSU Channel Islands, and our lab at CFDW. The goal we had was to establish monitoring baseline for aquatic resources in a remote, arid, and harsh environment. So just to get you organized here, Channel Islands National Park is off of the coast of Ventura and Oxnard. And Santa Rosa Island itself is the second largest island in the national park. You can see it highlighted there. Does this pointer work? Not really. Okay, that's fine. So a little bit about the island itself. It's about 83 square miles. It's about 26 miles from the coast. So it's in the middle of the ocean, and that will come into play here in a little bit later. And this is just all the different sites that we sampled on the island. You can see we pretty much sampled all areas of the island. Santa Rosa Island itself has got diverse geology and geography. The northern half of the island is this broad marine plateau with marine sediments that have uplifted, and the streams have cut down through those sediments. The southern part of the island is volcanic in nature. So kind of two different sides of the island. No paved roads at all on the island. And there's a long history of grazing back from the 1700s on the island up until about the 1980s. And that will come into play as well. So we had two main sampling events, 2017 and 2018. And then we went back to the island again in 2022 through 24. We wanted to establish 30 sites that we're going to do our monitoring on. And at those 30 sites, we did CRAM on every site. And then at a subsample of 10 of those sites, we also did our bioassessment monitoring, which is our BMI sampling and our PHAB. We did probe measurements, and that'll come into play also. It's the normal swamp statewide bioassessment protocols that we're using. And then in 2022 and 24, we went back and did another 30 sites. Some of the sites we did that second round were different because of safety issues and getting back to some of these sites. One of the measurements we did was CRAM. We haven't really talked about CRAM at this meeting. It hasn't come up too much, so I wanted to go over it a little bit. You don't have to have flowing water to do CRAM, which is ideal in Santa Rosa Island because there's not much water out there at all. There are 4 different submetrics that are used in CRAM, and 2 of them are kind of watershed scale metrics, and 2 of them are kind of reach scale metrics.
Buffer and landscape, so that's looking at the riparian buffer around the stream, and then the landscape above and below the site. And then hydrology is where does the water come from, okay, at your site? What's the main source of the water? And then we look at the physical structure, so the in-stream physical structure, and then we look at the biota. And those last two are reach scale, and those are going to be important in some of our analysis later. So one of the reasons is because those watershed scale metrics are the same for every site on the island. There's no humans out there basically except for National Park Service staff. There aren't any paved roads, there aren't any buildings. So really those two watershed scale metrics don't really help us differentiate between sites very well. So we calculated this biophys score for the sites, which are just those two bottom reach scale ones. And Andy Wren did this back in 2016 to help look at some differentiation between sites. So we did that in this as well. We sampled for BMIs and we did CSC calculations. I don't need to go through this whole thing. We've seen all this a lot. So we did CSCI scoring as well. Our PHAB measurements, we did a bunch of in-stream. We did our pebble counts. It's our normal swamp protocols. So all the PHAB stuff we do with our normal swamp protocols we did here. Pebble counts, flow diversities, habitat types, bank stability, all of those things we did at those 10 of the 30 sites. So in our data analysis, we use box plots for CRAM and CSCI scores to look at differences between sampling events. So one of the things we were wondering is, okay, after this 5 years or whatever, do the sites look better or do they look worse? So, or are they the same? And that's one of the things that the Park Service really wanted to know is, do these, once we got rid of those grazers, are things looking better? And that's one of the things that we're trying to talk about here. And then we use NMDS organizations on the bug communities to see how they separated out on the island. So results. Overall, the overall CRAM score was 76, the average, and the range was 60 to 91. Just using that overall CRAM score, 9 of the 64 sites indicated impairment. But when we looked at that modified metric, that biophys metric, 50% of the sites scored impaired. So you're seeing, really when you look at the reach scale on the island, you're seeing that impairment. So this is just a box plot showing year to year, or the differences between the first sampling event and the second sampling event on our CRAM scores. There really is no difference. I just wanted to show you what some of these sites look like. On the left, this is Cherry Canyon. And this is the area by where Beecher's Bay is and where the National Park Service housing and everything is. It's on the eastern side of the island and it's very vertical. So grazing was never happened in Cherry Canyon. And you can see the big oaks, all sorts of, the habitat is really good. It's really diverse. The in-stream channel habitat is still great. The one on the right is out on one of these marine plateaus where it's all grass and it was grazed. So that's kind of the difference in some of these sites. The results for the CSCI, again, scores range from 0.58 to 0.92. 77% of the sites showed impairment, and that's that 0.79 scale that we've been talking about. So most of the sites, or a lot of them, are showing impairment. Sites in Water Canyon, which I'll kind of point out hopefully on this map here in a little bit, scored highest overall, and we'll kind of talk about that. So thanks to Rafi with help for this. One of the things I wanted to point out here, so look at our colors. And we look at the blue is the South Coast CSCI scores overall. This is on the mainland. Green is the South Coast developed sites, and we're considering those sites that are developed based on urban and agriculture. And then your purple sites are the South Coast undeveloped sites. Your red is your Santa Rosa sites. Those fall almost exactly in line with South Coast developed sites. You would think, it being an island and no people being out there, that it should be closer to the undeveloped sites, but it's not. And it's because when you get in the channel, this is what the stream looks like. So you get all the way down from, they drop us off way up there at the top of that mountain, and we come down and get into the creek. And that taifa is 6 to 8 feet tall throughout the whole reach. So this, I put this up because I want to show the results from the physical habitat stuff. So percent vulnerable banks, 70%. Slow habitat, almost no riffle habitat. Shannon diversity of flow is very low. Lots of sands and fines, and a ton of coarse particulate organic matter. And it's from the taifa. It's not from a loxinous material coming in. It's from the taifa that's growing in that channel. And it's often 2-3 feet deep of taifa at the bottom of this stuff. So you have to dig down with your net and get to the water to take a sample. It's interesting. But all of these things are indicative of these grazing effects, these lasting grazing effects from all the grazing that happened on the island. So one of the other things that we did when we're doing our bioassessment sampling, we do probe measurements, right? And one of the probe measurements that we do is specific conductivity. And when we're out there in the field, we put the probe in there and we're getting 2,000 for our measurement. And usually it's 150 maybe in a stream. 2,000, we're like, what's going on with our probe? It's broke, right? It wasn't. That's what the conductivity is on the island. So the average was 1943 microsiemens per centimeter. Again, usually it's in the hundreds in a normal stream here on the mainland. All but one site exceeded possible impairment threshold, and that was Rafi had kind of developed that back in 2015. Salinity, the average salinity at a site was 1 part per 1,000. Normally in a stream on the mainland, it's 0 or 0.1. And 55% of the sites scored above that impairment threshold on the island. One of the other things we did, oh good, that showed up right. So this is an NMDS, and we're looking at the benthic macroinverted communities to say who looks more like each other, right? So I wish this pointer was working. Yeah, oh, okay, good. So it's not moving for you guys. It is for me, but it's not for you guys. Okay, so I'll just point it out to you. So what we've done, we put a map of the island up in the upper right, and we've put our site numbers on the island of where those sites are. So if you look at the two that are really close together, site 18 and site 2, those are in Water Canyon. And see where the green spot is on the map, 2 and 8, that's Water Canyon down there. Water Canyon has the most flow of any of these streams. So it's definitely perennial, and it's got the most volume of water. So those two sites, every time I put my hand close, those two sites in Water Canyon come out together. They're more similar to each other than they are to the rest of the island, right? And then the big group of sites, that group in that bigger bubble, are all in that northern plateau of marine sediments. And then all the other 4 sites are in their own little canyons on the south side of the island. So it depends on what watershed you are, will kind of determine what your benthic macroinvertebrate community looks like. So some conclusions, CSCI, PHAB, and reach scale CRAM indicate impairment at basically all sites. Inlet sites score within the range of mainland sites, but look most like SoCal developed sites impacted by urbanization and agriculture. Perfect. Impairment most likely is associated with legacy impacts from grazing, but lower scores may be related to that natural environment of the island as well. So future directions here, what we really want to do is we want to look at the biological communities on the island versus similar sites in, oh, I'm sorry, I'm still in conclusions. Okay. Biological communities similarly clustered within watersheds, sites in water canyon scored best for CSCI, and that's most likely due to the more perennial flow. And we have established a framework that we can monitor this stuff. So future directions, we want to look at these communities on the island versus similar sites on the mainland and see if really is it the grazing out there, or is it this harsh environment of the island that's causing these lower scores. So we want to look at sites with similar scoring CSCI sites, similar scoring CSCI scores, or sites that have similar environmental conditions, so salinity, specific conductivity, and flow regime too. One of the things Rafi and I were talking about is these streams are more like slow flow wetlands than they are rivers or streams. So that is our future steps. So thank you.
Thank you, Dan. Do you have any questions in the room?
Has anybody proposed anything to remove?
Oh, you turned it off. There we go.
Yeah, you're turning it off and on. No. So the question was, has anyone proposed any way of removing the typha from the streams? And the answer is no. So basically the National Park Service right now is treating Santa Rosa Island as, okay, it is what it is. It's going to do what it's going to do. In fact, they don't even want, they're reducing, they want to make it a, what do you call it, a wildlife protection area or something. And so they really don't want people going into the island and doing stuff anyway. So I know, but that's their policy. It's a hands-off policy. So it was really interesting because I thought that first year or the first sampling event, you know, I was thinking to myself, if we just get some really good rain to blow out this typha, right? Well, we did have good rain in 23 and 24, but it didn't do enough to get that stuff out of there. Yeah. More.
Thanks, Dan. Did you look at, was there a difference in the conductivity relative to the marine terraces and the volcanic side of the island?
Not specific. You know, I could go back and look exactly because we know which sites those are, right? But it was high everywhere. And yeah, I mean, the highest site was site 9. Oh, I don't have that map up. Site 19, which is on the southwest corner. That was probably our site. That and along with site 1, which is on the southeast corner there. Those were the closest sites to the ocean. And those had some of the highest connectivity. One thing we did some NMDS2 ordination first on conductivity. I didn't really have enough time to put that in this talk, but we'll put it in with our publication. But there are some ordination stuff with conductivity as well.
If I can chime in with an internet question, was there any correlation between CSCI score and flow type, perennial/intermittent? I wonder if scores for this project will change once more intermittent data is integrated into the CSCI score calculations as discussed in a presentation yesterday?
Well, so that's a really good question. So none of the sites on the island were used as part of the CSCI development data set. And so all the CSCI scores were from sites that are perennial. It's just that not all of them flow as well as Water Canyon. So we didn't do any BMI sampling on any non-perennial sites here. It would be interesting. One of the things I've always wanted to do is to go back to the island when there's flow in that Cherry Canyon site that you saw, that best scoring cram site. I would love to sample that. But that would be in the rainy season, and they usually don't allow people to drive on any of the roads in the rainy season because they're not paved. And they often wash out. One of the main roads that goes to the southeast side of the island, it's called Wreck Road, has been washed out for 2 years, so you can't even get to that side of the island anymore. But yes, if there is a modification, I would love to rerun some of this stuff. But remember, the CSCI scoring works well in Southern California anyways. So I think the scores are valid for this site, for these sites with our current model.
We have time for one more question.
I had a question for the invertebrates. If there's any endemic to the Channel Islands or Santa Rosa that could be
No.
adapted? Okay.
No, there's a subset of what's found on the island or on the mainland. And I mean, that's kind of another question, is this island biogeography, right? Are their scores a little bit lower because some taxa just aren't there, right? Looking at the CSCI scoring, that's not really the case. There are other taxa that are not used in the scoring that are present there, which you would find on the mainland too. So it's just a subset. Now there might be a new species of aphid, galling aphid on manzanita out there that I was helping one of my colleagues work on, but that's a bug geek thing, sorry. Anything else?
I think that's all we have time for. Thank you, Dan, for that wonderful presentation. Thank you. And since we're transitioning to our longer talks, I wanted to make room for our next speakers in the front row. If you guys can make room for them, and if you guys can make your way up front. I'm going to announce you, and then just press the middle button when you're ready. Dan wanted to thank everyone on this slide. Did you get to this slide?
Well, also Pete Odie.
And Pete Odie.
Helped me with a lot of the talk too. So thanks, Pete. I know you're welcome.
Thanks, Pete. All right, our next speaker is Isaac Owens. He's a master's student at CSU Bakersfield. His research explores macroinvertebrate responses to varying aquatic conditions. Isaac also mentors young men of color through the Budding Leaders program. So that was a nice fun fact that I wanted to add. And his presentation investigates the impacts of land cover changes on the diversity of macroinvertebrates in arid regions. So let's give Isaac a round of applause.
All right, is it on? Can you hear me? Yeah. All right. Thank you for the great introduction. Yeah, so we're going to be talking about macroinvertebrates. But before I start, I would like to acknowledge that the land that the research is being conducted on is the traditional land of the Tohono Indian tribe. We are grateful for all the indigenous people who continue to care for and remain interconnected with these lands. Through research and conservation efforts, we promise to be conscientious stewards of these lands for future generations. Now, let's start with freshwater. Freshwater ecosystems support a suite of flora and fauna. For example, you could look towards the southeastern part of the US, which is a hotspot bivalve for bivalve biodiversity. You'll look also towards the headwaters of the river systems in Alaska as it supports salmon when they're starting to reproduce. You could also look towards the Florida Everglades as it supports a vast majority of aquatic plants. But these freshwater ecosystems are also crucial resources for human societies. We use freshwater for drinking and municipal needs. We also use a ton of freshwater for agricultural use. And we also use freshwater ecosystems for recreation, for having a little bit of fun. And a subset of these freshwater ecosystems are headwater streams. Headwater streams are the beginning of river networks, and they comprise over 53% of the river networks in the US. And they're supported by a lot of inputs from stream-side vegetation, so a lot of allochthonous inputs. And they connect to different habitats within and throughout watersheds. Now, I know I've been preaching to the choir. I know you guys are all familiar with freshwater ecosystems and et cetera, but just in case, you know, somebody's watching who is not familiar, well, I'll explain a little bit about aquatic macroinvertebrates. So aquatic macroinvertebrates use both leaf litter as food and habitat. For example, on the top right picture is a caddisfly, which does so. And we can classify these different macroinvertebrates into different functional feeding groups. So you have shredders, collector-gatherers, grazers, collector-filterers, and predators. And we could also, some of these macroinvertebrates are indicator species, just meaning that if you have a lot of these indicator species inside your stream, means that your stream is probably doing pretty well, functioning pretty well. And we can predict where these macroinvertebrates are based on the surrounding vegetation that's inside your stream. For example, these are two pictures of the same stream, Tohon Creek, the stream that I'm researching. On the left, you have a picture of the valley. As you can see, it's a lot more open, a lot more sun being able to, sunlight to enter the stream, a lot more opportunity for aquatic plant and algal growth. And on the right is a picture of the stream in the mountains and the high elevations. As you can see, a lot more shade that's being created by all those tall trees, a lot of opportunity for leaves and sticks to fall into the stream. So it brings me to my research question of how do stream energy resources in aquatic macroinvertebrate communities change between mountain and valley habitats? So I predict that there'll be more terrestrial energy resources, so leaves and sticks, in the mountain habitat. And as you move further down to the valley, the energy resources will shift to inside the stream, so more aquatic plant and algal growth. I also predict that there'll be a predictable macroinvertebrate community shift linked with these energy resources. Specifically, I predict that there'll be more collector-gatherers and shredders in the mountains. And as you move further down to the valley, the community will shift to more herbivores and collector-filterers. So where is Tohon Creek? Tohon Creek is about 6 hours away from where we are right now, 6-hour drive. And Tohon Creek, the mountain habitat starts at an elevation of 2,300 meters above sea level, and it's surrounded by a lot of pine species and a lot of oak species. And as you move further down to the valley, it starts at an elevation of 480 meters above sea level, and it's surrounded by a lot of willow and cottonwood species. And overall, Tohon Creek, sorry if it's echoing, is about 45 kilometers long. So this is a closer picture of Tohon Creek. And as you can see, we selected 12 sites. We have 6 in the mountain habitat and 6 in the valley habitat. And we collected data back in June of 2024. We collected stream energy resources, so allochthonous and autochthonous resources. We collected water samples for nutrient analysis. We measure water physiochemistry parameters. We collected macroinvertebrates using a Serber sampler. And we use a densitometer to measure canopy cover. So I have some data to share with you. These are univariate regression analysis, but in the future I will be doing further analysis. I wanted to share a little bit with you guys. So This is what we got so far. So we'll start off with canopy cover and light intensity. As far for elevation, canopy cover, elevation was not a significant predictor for canopy cover. However, light intensity was, with the trend being that as you move further up in elevation, you have less light entering the stream. As far as temperature and dissolved oxygen, elevation was not a significant predictor for either temperature or dissolved oxygen. But for our nutrients, orthophosphate, ammonia, and nitrite, elevation was not a significant predictor. However, elevation was a significant predictor for nitrate, with the trend being that as you move further up in elevation, you start to see more nitrate. For stream width and stream depth, which is surprising, is as you move further up in elevation, elevation is not a significant predictor for either of these. But for substrate size, elevation is. As you move further up in elevation, you start to see the substrate size increase. So a lot more stones, a lot more boulders. Now, this is a table of all the taxa that were collected. I know it's a lot. It's probably hard to see up there, but I'll point out all the important stuff. So we have 17 unique species in the mountain habitat. We also have 12 unique species in the valley habitat. And then we have 18 shared species between both mountain and valley habitats, making it a total of 47 species altogether. And you can't really see, but I did kind of highlight that the mountain had a higher species richness compared to the valley. Now there is a macroinvertebrate that we could not add to the table, but I think it's pretty cool. We have Helicopsychidae. We collected their shell casings, but nothing was, there was nobody home, so we didn't have, we didn't have the macros inside the casings, but we did see the casings, so that was pretty cool. So this is the same table, but a little bit more blown up of the taxa that dominated both mountain and valley habitats. We have Betidae and Chironomidae. We also have Simulidae and Hydropsychidae. We also have Oligochaeta and Nemoridae, and also Acarian. As far as macroinvertebrate density, elevation was not a significant predictor for macroinvertebrate density. Now this is a relative abundance figure. Most of you guys probably have already seen this before. But yeah, this is a relative abundance figure of showing all the functional feeding groups between both mountain and valley habitats. And on the top, I included the total counts of macroinvertebrates that were collected in both habitats. And as you can see, in the mountain, it's more than double the amount of macroinvertebrates in the mountain compared to the valley. And I ran a chi-square, and it showed that the macroinvertebrates were unique between both mountain and valley habitats. Oh no, it's messing up. Something shifted, I don't know. The functional feeding groups that dominated both mountain and valley habitats were collector-gatherers and collector-filterers. We also see that there was a higher amount of relative abundance of predators in the valley compared to the mountain. Same being with the detritivores. We saw a higher relative abundance of detritivores in the valley compared to the mountains, but we did see a higher relative abundance of shredders in the mountain compared to the valley. Now, this is another relative abundance figure, but now for taxa, I ran a chi-square again, and the communities were unique between both mountain and valley habitat. And the most dominant taxa were Betidae, Simulidae, hydrocyclase, and chironomidae. So let's return to my research question of how do stream energy resources and aquatic macroinvertebrate communities change between mountain and valley habitats? As far as stream energy resources, if you were at Puerto Rico for SFS, I said I was gonna have this data for you guys, but I promise if you go to the SFS in Spokane, I will have that data for you. As far as canopy cover, their elevation was not a significant predictor, however, light intensity was. We might not see a significance in canopy cover because in the valley, there's a lot of tall shrubs and a lot of tall grasses, so maybe that's why we don't see a significance, but still interesting overall. As far as temperature and dissolved oxygen, elevation was not a significant predictor. A reason we may not see a significance in dissolved oxygen is because lower in the valley, there may be more aquatic plant and algal growth that is producing that oxygen. So that's possibly why we don't see a significance. As far as our nutrients, the only one that was significant was nitrate, with the trend being that as you move further up in elevation, you do see an increase. That could be the vegetation that surrounds the stream in the higher elevations might have a little bit more of a nitrogen, higher nitrogen content, but I will look at that in the future. As far as stream width and stream depth, there was not a elevation was not a significant predictor. This could be because Tahone Creek is not large enough to get to that size where you start seeing the change in width and depth. So that could be the case. As far as substrate size, we did see elevation was a significant predictor. You could even see in the picture how in the valley there's a lot more sand, and then as you move further upstream, you start to see a lot more boulders and stones. As far as our macroinvertebrate community, there was a unique community between both mountain and valley habitats, so that was pretty cool. And with that, I'd like to acknowledge my thesis committee, my advisor, Dr. Ray McNish, my collaborator, Tahone Ranch Conservancy, the entire McNish Aquatic Ecology Research Lab. I appreciate them going through all the samples. It takes some time. I do appreciate you guys, and all the funding opportunities that allow me to do this research. And are there any questions?
Thank you, Isaac.
Thank you. Go Rams. 49ers.
No.
There's no questions. I'm okay with that as well.
Don't we love that? No questions in the room? Any questions online? Oh, wow, okay, thank you.
Yeah, just curious if flow was different and if that had any influence that you.
Yeah, that we didn't measure flow, but that could be something that affects it. But just like eye test, there wasn't too much difference, but we did not measure that.
I think that's really neat.
Thanks.
Did you see like a gradual shift in the BMI communities as you went from like upstream to downstream, or was there kind of a harsh change at any point?
Not really. I mean, the beta days really like dominated throughout, so not really.
Did you go further than family in your idea?
No, all the way down to family, but yeah, not genus. No.
Okay, thanks.
Hmm?
really good talk. And I was wondering, you kind of hypothesized that you'd see more of like the grazers, herbivores
Yeah.
increasing in the valley, and it didn't seem like you saw that. I was wondering what you thought that piece. Why?
Yeah, it could just be, I'd still need to get that energy resource data to you guys. So that could be something that we just don't see a lot of different aquatic plant and algal growth in the valley. But yeah, so I think that would be the main factor showing that.
I was just gonna say that could be related to particle size.
Mm.
Much more sand and fines in the valley, so algae not gonna grow and that stuff.
Good point.
Oh,
All right.
sorry, one just came in on Zoom. Were the benthic macroinvertebrates, sorry, came in as an acronym and my brain was calculating. Were the invertebrates collected both upstream and downstream? If not, how was it determined along the stream where to collect?
Oh, yeah, it was collected both upstream and downstream, and we decided where to collect based on ease of access, where the roads were a little bit closer to the stream. We didn't want to be walking too crazy, too crazy with all the equipment, but yeah, and areas where there were riffle habitats. Hmm?
All right, thank you, Isaac.
All right.
Good job.
Thank you. Appreciate it. Bye.
Thank you. Next up, we have two presenters. So we may need two mics. All right, our first presenter is Molly Valerio. She manages the BMI lab at Sierra Streams Institute. Molly has a bachelor's degree in zoology. Fun fact, she was born and raised in England, and she moved to California in January 2024. So let's make sure we welcome her. Jessica Herman is our second presenter. She's a biologist for the BMI and water quality labs at Sierra Stream Institute. She has a master's degree from Boston University in ecology, behavior, and evolutionary biology. She enjoys studying historical changes to riparian habitats and community structures in order to inform targeted monitoring and restoration. Together, they will educate us on a more humane preservation method for our benthic aquatic insects. Wait, which one is it?
Yeah, you got it.
Keep going. Oh, it's this one. Thanks.
All right, thank you for joining us today. My name is Jess. Oh, is the green on? Or am I just talking really quietly? Okay, thanks. Is that any better?
Yes.
Okay, thank you. Yeah, my name is Jess. I'm lead river scientist for Sierra Streams Institute, and
my name is Molly. That's really loud.
Let me turn yours off, Molly. Okay.
Well, then how am I going to?
Okay, so we'll have to alternate. So when Molly is speaking, maybe you can turn yours off, Jessica.
Sure.
So just press that middle button.
Okay, thanks. All right, so we're going to be talking a little bit today about a new method that we kind of started to implement in our most recent field work and the bioassessments that we've done starting this summer, trying to find a more
humane collection method for when we collect BMI from the streams. So less of a technical presentation, more of just kind of a share out. But first I wanted to give some background on Sierra Streams Institute. We are an environmental nonprofit. We're based in Nevada City, and we were established 30 years ago as of this year. Sorry about that. I'll try this. Is that any better? Testing. Okay, cool. I'll just hold it. Okay. All right. No. All right, so Sierra Streams is a community-based participatory research organization. We have different programs that span from monitoring to restoration to forestry and education. Specifically, our long-term monitoring program has historically focused on the ecological health of the local Sierra Nevada foothill watershed. Our focus has been in Deer Creek for the past 30 years, which is a tributary to the Yuba River. And in more recent years, we've also expanded into the Bear River. And as of the summer of this year, we've further expanded into the northern and central Sierra. So our monitoring program covers bioassessment as well as environmental and water quality data collection and analysis. And here's kind of a map showing where we're located in Nevada County, and some of the watersheds that we cover. Okay. And so I just wanted to give some additional background on our motivation for this project. As everyone in the room probably already knows, the use of BMIs or benthic macroinvertebrates as key biological indicators of watershed health is basically bioassessment. And it's also common practice when collecting BMIs from streams to immediately transfer the BMI samples to ethanol for quick preservation in the field. So this is kind of a study that was motivated off of Molly's experience and my experience doing this for our jobs, as well as past research experience working with insects and other laboratory and research settings. And we also receive feedback from other staff, volunteers, and interns who work with us, kind of voicing some discomfort with this practice of immersing bugs in alcohol and watching them kind of squirm until they ultimately perish in alcohol. So we wanted to see if there was something that we could easily implement that would reduce the stress response of the insects that we are handling and taking from the creek. And one of the things that we found out early on was that there's kind of a scarcity of documented research on how invertebrates, particularly insects, experience stress and perceive pain. There aren't really a lot of documented best practices around the ethics for minimizing stress due to handling and preservation. So kind of digging a little bit deeper, this is a figure that was pulled from a study that we referenced for our own pilot study. This is a 2024 paper by Carter et al. And it's basically showing differences across behavior, physiological, cellular, and hormonal markers of stress in echinoderms that were exposed to 4 different types of anesthetic solutions. Specifically, they were testing these anesthetic compounds on sea cucumbers. So they tested ethanol, magnesium chloride, eugenol, and TMS. And for those who aren't familiar with all these different compounds, eugenol is a derivative of clove oil. And it is commonly used as an narcotizing agent for aquatic invertebrates. And TMS similarly is another narcotizing agent that is usually used in aquarium settings for anesthetizing and euthanizing fish. Okay, so figure 2 on the left shows respiratory rates after a 20-minute timed exposure to each of these various different anesthetics versus the control in black. Thanks. Can you hear me better? Okay, cool, thank you. And figure 3 on the right shows cortisol levels after 20 minutes timed exposure in each of these anesthetics. And then panel B, or the bottom half of that figure, shows post 20-minute anesthetic exposure plus 1 hour exposure to a predator or some kind of environmental stressor. And so by and large, what the authors found was that ethanol elicits a heightened stress response in aquatic invertebrates, and there were mixed results seen with magnesium chloride, which is kind of shown in the orange bars, and then more consistently, exposure to both eugenol and TMS to varying degrees seemed to decrease the stress response seen in these aquatic invertebrates that they tested these compounds on. So that motivated us to investigate further and look into the effects of eugenol and TMS as potential narcotizing agents that we could use for the BMIs that we collect in the field when we do our summer stream surveys. So again, to recap, we wanted to answer this question. Can we reduce the stress response of macroinvertebrates that we collect in the field? We wanted something that was practical in terms of time, cost, ease of use, and ease of replicability. We also wanted something that would be effective for the diverse range of macroinvertebrates that we commonly find in our samples. And so we tested these 2 different anesthetic agents, eugenol and TMS, which is also sometimes referred to as MS-222. And we had kind of a general way of quantifying response to anesthesia that were somewhat limited by the means that we had to test these right before our summer sampling. We wanted to know the relative effectiveness of these different anesthetic compounds after a 15-minute timed exposure to see which taxa responded and which did not. And then post exposure to each of these anesthetic agents, we wanted to also know if the BMI would recover once placed back in creek water. And we also had a qualitative approach to measuring stress, which Molly will talk more about.
All right, perfect. So we've only got a few more minutes left for this presentation. I can see somebody nodding off. Let's get through this today together. So we've got the methods that we did is basically we just collected the BMIs from the creek. We chose a study site that we know from our previous sampling has good diversity of BMI. As one of our things that we wanted to test was if this would work on all the BMI that we collected. So we collected the BMIs and then we placed them in the anesthetic solution of either TMS or eugenol, and we recorded if they were moving after every 3 minutes or 15 minutes, and then we moved them into some creek water for recovery before releasing them back into the creek. On the screen, you can see some of the different concentrations that we tested. And we really wanted to see if we could induce a rapid anesthetic response so that it would be easy for field crews to implement this into your collections. Some of our preliminary results were, we found that they both did work as anesthetics, and they were equally effective, which was great. Generally, the smaller BMI were anesthetized faster than the larger BMI. However, we will see some exceptions to this. The Ephemerella day mayfly and adult coleoptera took the longest to anesthetize at any of these concentrations that were previously shown. I'm not entirely sure why there were these differences in these 2 particular taxa. So that raises some really interesting questions on taxon-specific morphology and how different BMIs interact with the anesthetics. On the flip side, we also found that the damselflies did not survive 15-minute immersions, and so unfortunately some of them did die. However, all other taxa did survive the 15-minute anesthetic bath that we put them in. So there didn't seem to be too much difference in the specific concentrations that we tested, and so we decided to move forward with 1.4 grams per liter of eugenol solution in our field studies. some of the bugs, as we saw, did not respond to anesthetic. And so we did try a nuclear dose on these like ephemeralidae mayflies that we found. We did 133 grams per liter, which is like 100 times more than what we found, just to see if this anesthetic would actually work on all of these BMIs, and it did. So they did anesthetize, so that's great. We also didn't find any large Megaloptera species, which we were hoping to find at this site, and so we would have to see how they responded to that in the field. So here we have a video of us collecting in the field BMI, which should hopefully take us to the video. Or I don't know if it's going to come up. Right click on. Need to share this. Oh, sorry. Nice music though. Did you want to include the audio as well? Doesn't have to Okay, cool. So okay, fine. So here we're collecting BMIs in the field using eugenol. We found that it was a really effective way of anesthetizing BMIs in the field. We collected 36 BMI collections over this summer, all of which incorporated using eugenol. We found that it was really easy for field crews to implement into the field and didn't add much extra time at all onto the collections and their time, so it wasn't a big ask for them to implement this. After they were anesthetized in the eugenol, we then transferred them into 70% ethanol for preservation, and then once we got back to the labs, we then transferred them into 80% ethanol for preservation long term. So yeah, so you can see that we're just like using all the equipment that we would typically be using in the field, and it really wasn't much extra ask to do this. We did find that, well, as we mentioned earlier, we didn't have a chance to test it on the large Megaloptera in our pilot study, and we found that there was one case where Megaloptera was not anesthetized at 1.4 grams per total concentration. So they would require that like nuclear dose or a higher concentration in order to anesthetize them. This method is also super flexible. Our crews would wait for like 1 hour before they're putting them into the ethanol for preservation. So they'd be in the eugenol for 1 hour, and that allowed just like really consistent like anesthetic. And a lot of the BMI did also die in the anesthetic before going into the eugenol after 1 hour, but like, hey, they didn't really, I don't know, didn't think that they felt much, so was probably a nicer death than going into the eugenol, that's for sure. Do you want a presenter? Oh, no. Do you need your presenter? Maybe nice, if possible, but it's okay. Well, yeah, while we're getting the PowerPoint up, you know, one of the reasons that really motivated us to do this study was the feedback from volunteers, interns, and staff that they were not comfortable collecting BMIs and seeing them suffer in the eugenol for preservation. And so we asked people for some feedback, and we got really positive feedback from different folk around the use of an anesthetic step before eugenol. For example, like Melissa Grimm from our SSI chemistry lab manager said it makes her feel way better about bug collection and the preservation process. And we also found that as we were hiring for our in-house bug lab this fall, it was mentioned on job applications that this is one of the reasons why people were attracted to apply for SSI jobs, was because we were prioritizing the minimizing invertebrate pain.
Oh, and some of you probably know Dave, or Dave Herbst is a research scientist with Snarl. He's also worked with UC Santa Barbara and works with UC Santa Cruz, and he acts as board VP at SSI. He also commented that this strikes him as an essential step that hasn't traditionally been part of the work, and just commented on the sacredness of life that we're taking from the creek. So that was kind of cool. He also advised a little bit on this pilot study.
Yeah, so just really quickly to wrap up, I know we're eating into our question time right now, but we wanted to consider some future directions for this work. And firstly, considering whether collection and preservation of BMI is even necessary for the data that you're trying to collect, or whether we could consider field picks as a better method of collecting data, for example, in some restoration projects that maybe don't require the same level of like taxonomic identification that would be necessary with preservation and collection. You could just go to that order and family level with field picks.
We also wanted to acknowledge that we didn't do any tests on the cellular or molecular markers of stress to really robustly test this method. So that could be another future direction, looking also at relationships between morphology and life stage and that kind of relationship with the efficacy of the different anesthetic solutions, specifically in insects that are handled in research and lab settings.
We'll probably skip this page. So yeah, thank you everyone for listening, and hopefully you will consider using an anesthetic step in your collection of BMIs. And we hope that this presentation will start the conversation around a more humane and ethical collection in bioassessments, and continue a conversation around how researchers treat our animal counterparts with due respect. Thank you very much. Any questions?
Thank you, Molly and Jessica.
Hi. So I really appreciate you taking into consideration the suffering that insects might have, because most people don't care about the sufferings of macroinvertebrates. They don't even think they can suffer. I just wanted to add that I read a relatively recent study which suggests that insects could actually feel nociception, which is pain. And I think that might be another direction this research could go into, to see if ethanol could cause insects to feel pain when they're being preserved, or maybe even if the anesthetics have any effect on nociception as well. Just thought I would say that.
Yeah, thank you. That's a great point. Unfortunately, we weren't able to test that ourselves, but definitely.
So my question is just for IDing purposes. Did you find that anesthetizing them before preserving them helped in your IDing?
So we haven't got around to the ID work yet, because these are just collections. These are just collections from 2025. It's common practice with other invertebrates to anesthetize them before killing them for like better preservation of like tissues and muscles. And so we hypothesize that it will make the ID better, because as we know, like BMIs are really easy to break apart in your sample when you're going under them, like looking at them under the microscope. And so hopefully we will see more intact BMI. But yeah, we're getting to that this winter. Yeah.
Very cool talk. Thank you. I've previously worked at a research-focused veterinary hospital. And so seeing a lot of the human impacts of compassion fatigue around euthanizing mammals and whatnot, it was obvious how big of an impact that had on staff and volunteers. So I think you looking at this for not only the invertebrates, but for field workers is very cool. And I'm wondering if there was any observation period incorporated into your data collection for when the invertebrates were in ethanol after being anesthetized?
Yeah, we didn't do that in our pilot study, but for the 36 collections over the summer, we observed them. And as I alluded to, we only saw one megaloptera that was not anesthetized after 1 hour immersed. And otherwise, there wasn't any movement or obvious signs of distress from the BMIs.
Just a couple of comments that you may want to take into effect. Beetles probably will not get anesthetized because they breathe off the surface, not through gills. And if you want a poor man's method of TMS, try Alka-Seltzer.
Thank you. That's interesting. We hadn't heard about the Alka-Seltzer method. Yeah, we did notice that a lot of the water pennies did not succumb to the anesthetic, and we were thinking that that was probably the reason. Yeah.
Do you look at any non-insects?
No. Well, we collected the BMIs, so not just insects, but also we had all the invertebrates, so oligochaetes and ostracods and all the squibbly wibblies that aren't insects. So yeah, they all responded similarly. As we said, like there was only the one megaloptera in our summer collection that did not respond, but everything else looked anesthetized to us.
And our method that we kind of based the pilot study off of was kind of based on a wide range of research done on other non-insect aquatic invertebrate species. So we looked at papers done with similar experiments done on grass shrimp, ostracods. Can you remember what else? Like we looked at those echinoderms in that Carter paper that we referenced.
Hi. Great talk. I'm really glad that you're opening up conversations around ethics. Invertebrates often get put just through the cracks in that in a lot of ways. So my question for you, coming from as a marine benthic ecologist, usually formalin is the first step before ethanol. I don't know if that's normal in stream environments, but I was wondering if you have any sense of if that is a more humane, instantaneous death type of way to go for or not necessarily an insect, but still a BMI, just a marine one. Or if you would recommend looking into anesthetics for those procedures as well.
Thank you. I don't remember specifically reading about the use of formalin as an anesthetic agent. If I remember correctly, I think we did run across a paper that discussed it as a less humane way of or method for euthanasia of aquatic invertebrates, but I'd have to double check that paper. Yeah, I mean, I've done aquatic or like, what am I trying to say? I've participated in a lab in the past where we use clove oil, which is basically the same thing as eugenol, to anesthetize aquatic invertebrates, specifically marine aquatic invertebrates, but I'm not so familiar with formalin.
So we have some experience with formalin. I used it as a graduate student studying the life history of isogenoides in the Rocky Mountains. And we made a solution called Kale's solution, which is isopropyl and formalin and water, I think. There's a third component to it. And the formaldehyde for invertebrates is for preserving color pattern, which is a taxonomic character generally, not so much in Plecoptera, but I used it to keep the pigment pattern for illustration because I was revising a whole genus. So maybe not for humane purposes, but for preservation.
Yeah, I think the overall well, firstly, thank you. I didn't know about formalin preserving color, and that's something that's super interesting. Definitely want to look into that actually. But yeah, I think the main takeaway from our talk is to sort of open it up to everyone to figure out the best technique for themselves and their collection techniques. This is what has worked for us, and it's not going to be a catch-all, and that this is as flexible, is flexible in what anesthetic you can use, and to find one that works for you and your field work.
And that makes time. Thank you again, Molly and Jessica, for your presentation. It's almost time for lunch, everyone.
Yeah, I mean, we ended up at just past 12:20. So just a few reminders before you all go your separate ways to find Alexandra in the back there. If you have your cash donation for the R workshop, again, SafeIt workshop, meet in the lobby 115, SAFIT workshop in the lobby 115. And the R workshop is going to be Klamath rooms. That way you'll go across a little footbridge and it's kind of in the corner there. And that's it. Thank you all. Thanks to everybody, presenters, you all. We'll see you all next year. Our workshop starts at 1:30. Yes.